Deep beneath the border of France and Switzerland, within a 27-kilometre circular tunnel, the Large Hadron Collider has for years accelerated particles to near-light speeds, confirming predictions and discovering particles exactly as theoretical models anticipated. Recently, however, analyses of collision data from the latest experimental run have revealed signals that defy the current understanding of physics. Initially observed as statistical blips, these anomalies grew increasingly persistent as more data was collected, resisting conventional explanation. What began as cautious curiosity among a small research team has now emerged as a potential challenge to the standard model. Multiple independent detectors are recording the same unexpected phenomena, with statistical significance surpassing thresholds that the field considers compelling. These signals suggest violations of fundamental principles long assumed inviolable. Unlike a single anomalous particle, the emerging pattern points to broader inconsistencies in our understanding of the fundamental forces, raising the possibility that current theoretical frameworks may require substantial revision to accommodate the new observations. The unexpected resonance at 95 giga-electron-volts. When particle physicists analyze collision data from the Large Hadron Collider, they are looking for what they call resonances. These are peaks in the data that appear at specific energy levels, indicating the brief creation of a new particle before it decays into other particles. The Higgs boson, discovered in 2012, appeared as a resonance at 125 giga-electron-volts, exactly where decades of theoretical work predicted it would be. Resonances are the signature of particles, the evidence that something existed for a fleeting moment during the violent collision of protons, travelling at 99.9999% the speed of light. Every particle has a characteristic energy at which it appears, determined by its mass through Einstein's famous equation E equals mc squared. When you see a resonance at a particular energy level, you are seeing evidence of a particle with a corresponding mass. In early 2024, physicists analysing data from the Atlas detector noticed something unusual. A resonance was appearing at approximately 95 giga-electron-volts, an energy level where no known particle should exist. At first, the signal was weak, barely distinguishing itself from background noise. Background noise in particle physics refers to all the random fluctuations and well-understood processes that create a constant stream of signals in the detectors. Separating genuine new physics from background requires enormous amounts of data and careful statistical analysis. The initial observation at 95 giga-electron-volts had a statistical significance of about 2 sigma, meaning there was roughly a 5% chance it was just a random fluctuation. In particle physics, that's not nearly enough to claim a discovery. But as more data accumulated through hundreds of trillions of additional collisions, the signal didn't disappear. Instead, it grew stronger. By mid-2024, the statistical significance had reached 3.5 sigma, reducing the probability of it being a random fluctuation to less than 0.05%. Multiple analysis teams independently examined the data using different methods and different assumptions about background processes. All of them saw the same peak at 95 giga-electron-volts. The CMS detector, operating independently from Atlas on the opposite side of the LHC ring, began reporting similar observations. When two completely separate detector systems see the same anomaly, physicists start paying very serious attention. The problem is that there's no particle predicted to exist at 95 giga-electron-volts. The standard model, which describes all known particles and 3 of the 4 fundamental forces, has no placeholder for anything at this energy level. Every particle that should exist according to the standard model has already been discovered. The model's predictions have been tested to extraordinary precision over decades of experiments at particle accelerators around the world. It works. It works remarkably well, but it also has known limitations and gaps. It doesn't explain dark matter. It doesn't include gravity. It can't account for the matter-antimatter asymmetry in the universe. Physicists have been searching for physics beyond the standard model for years, hoping to find new particles or forces that might address these gaps. A resonance at 95 giga-electron volts could represent several possibilities, none of them simple. One option is that it's a previously unknown composite particle made of quarks. Quarks are the fundamental building blocks that combine to form protons, neutrons, and dozens of other hadrons. The recently discovered tetraquarks and pentaquarks demonstrated that quarks can arrange themselves in exotic configurations beyond the simple 3-quark baryons and 2-quark mesons. A new exotic hadron at 95 giga-electron volts wouldn't break the standard model, but it would be surprising. The energies and quantum numbers would need to work out in very specific ways, and preliminary analysis suggests the decay patterns don't match what's expected for a conventional hadron. Another possibility is far more exciting and concerning. The resonance could be evidence of a new fundamental particle entirely outside the standard model. Supersymmetry, one of the leading theories for physics beyond the standard model, predicts the existence of partner particles for every known particle. These supersymmetric partners would have much higher masses than their standard model counterparts, which is why we haven't detected them yet. A particle at 95 giga-electron volts would actually be quite light for a supersymmetric particle. Most theoretical predictions place them at much higher energies, but some models allow for lighter versions. If the 95 giga-electron volt resonance is a supersymmetric particle, it would be the first direct evidence for supersymmetry, one of the most sought-after discoveries in modern physics. There's also the possibility that this resonance represents something even more exotic. Some theoretical frameworks propose the existence of additional Higgs bosons beyond the one discovered in 2012. The standard model requires only one Higgs boson to give particles mass, but extended theories like the 2 Higgs doublet model predict multiple Higgs particles with different masses and properties. A lighter Higgs boson at 95 giga-electron volts would require significant modifications to existing theory, but it's not impossible. Other theories suggest the existence of dark matter particles that could be produced in LHC collisions under certain conditions. If dark matter particles can interact with ordinary matter through some unknown mechanism beyond gravity, they might leave detectable signatures in the collision debris. What makes the 95 giga-electron volt resonance particularly troubling is its decay pattern. When particles decay, they transform into other lighter particles in ways determined by the fundamental forces and quantum mechanical rules. The Higgs boson, for example, decays into bottom quarks, W and Z bosons, tau leptons, and photons in proportions that match theoretical predictions. The resonance at 95 giga-electron volts appears to decay into bottom quarks at a higher rate than any known mechanism would predict. The branching ratio to the ratio of how often a particle decays through one channel versus another is significantly different from what physicists would expect for any conventional particle. This suggests that whatever is creating this resonance has coupling strengths to quarks that don't match the standard model. The energy level itself is also puzzling. At 95 giga-electron volts, this hypothetical particle would have a mass about 75% of the Higgs boson's mass. That's a very specific value, and in physics, specific values usually mean something. They often indicate relationships between particles or constraints from symmetries in the underlying theory. Physicists have been working backward from this observation, trying to determine what theoretical framework could produce a particle at exactly this mass, with exactly these decay properties. So far, no single theory fits all the observations cleanly. Every attempt to explain the resonance requires introducing new assumptions or modifying existing frameworks in ways that create other problems. The experimental teams are being extremely cautious about these results. The history of particle physics includes several cases where apparent discoveries later turned out to be statistical fluctuations or systematic errors in the detectors. The most famous recent example was the apparent 750 gigaelectronvolts diphoton excess observed in 2015, which generated enormous excitement, before additional data showed it was just a statistical fluke. Physicists are determined not to repeat that embarrassment. They're subjecting the 95 gigaelectronvolt signal to every possible scrutiny, checking for instrumental effects, calibration issues and subtle biases in the analysis procedures. Independent teams are analysing the same data using completely different software frameworks. Theoretical physicists are examining whether any known standard model process could produce a fake signal that mimics a resonance. As of the latest data releases, the resonance persists. The statistical significance continues to grow slowly as more collision data is accumulated. The signal is now approaching 4 sigma, meaning there's less than a 0.01% probability it's a random fluctuation. That's still below the 5 sigma threshold that particle physicists require to claim a discovery, but it's getting close. If the trend continues and the signal reaches 5 sigma with no explanation in terms of known physics, CERN will face a profound question. They will have discovered something that our best theory of fundamental particles says shouldn't exist, emerging from the most precisely tested and successful framework in the history of science. Anomalous decay patterns in proton collisions. Inside the Large Hadron Collider, protons don't simply collide like billiard balls. Each proton is a seething mass of quarks and gluons, collectively called partons, held together by the strong nuclear force. When 2 protons collide at high energy, it's actually individual partons inside each proton that interact. A quark from one proton might strike a gluon from another, or 2 gluons might collide, or various other combinations. These parton-level interactions are what create new particles in the collision debris. The exact mixture of collision types depends on the internal structure of the proton, which is described by parton distribution functions derived from decades of scattering experiments. Every collision produces a spray of particles flying outward in all directions. The detectors surrounding the collision point are designed to track these particles, measure their energies and momenta, and identify what they are. Charged particles leave curved tracks in magnetic fields. Neutral particles, like photons, deposit energy in calorimeters. Muons penetrate deep into the detector before being stopped. By reconstructing all these signals, physicists can work backward to determine what particles were created in the immediate aftermath of the collision, and, crucially, what heavier unstable particles those decay products came from. This process is called event reconstruction, and it's where the recent anomalies have become impossible to ignore. Standard model processes produce particle decay patterns with well-understood rates. When a top quark is created, it decays almost exclusively into a bottom quark and a W boson. When a W boson decays, it transforms into either a lepton and a neutrino or a quark-antiquark pair with specific probabilities. These branching ratios have been measured in thousands of experiments and match theoretical calculations to better than 1% precision in most cases. The standard model's predictions for decay patterns are among its most precisely tested features. Any significant deviation from these patterns would indicate new physics affecting how particles interact and transform. Beginning in late 2023, physicists analysing LHC-RUN-3 data noticed that certain decay channels were occurring more frequently than predicted. Specifically, processes involving the production and decay of pairs of bottom quarks were showing up at rates 10 to 15% higher than standard model calculations suggested. This excess appeared across multiple different production mechanisms. it showed up in events where bottom quark pairs were produced directly from gluon fusion. It appeared in events where they came from the decay of heavier particles. The excess was consistent across different collision energies and different detector subsystems. A 10 to 15% excess might not sound like much, but in particle physics, where predictions and measurements often agree to within fractions of a percent, this is a massive discrepancy. To put this in perspective, imagine you're conducting chemistry experiments where you can predict reaction yields to within 1% based on established theory. Then suddenly, one particular reaction consistently produces 15% more product than it should. You would immediately know something important is happening that your theory doesn't account for. That's the situation physicists are facing with bottom quark production at the LHC. The first hypothesis was systematic error. Perhaps something about the detector's efficiency for identifying bottom quarks had changed. Bottom quarks are identified through their distinctive decay signatures. They travel a short distance from the collision point before decaying, creating a secondary vertex that can be distinguished from the primary collision vertex. Sophisticated algorithms analyze the detector data to identify these secondary vertices and tag events containing bottom quarks. If these algorithms were somehow tagging events incorrectly, or if the detector efficiency had changed, it could create a false excess. Extensive calibration studies ruled this out. The bottom quark tagging algorithms were tested using control samples of known processes where the production rates are precisely measured. The efficiency remained consistent with previous runs. Multiple independent tagging algorithms produced the same results. The detector hardware showed no anomalies that could account for the excess. When the same analysis procedures were applied to events that shouldn't contain excess bottom quark production, the results matched standard model predictions perfectly. The excess appeared only in specific channels, which argued strongly against a detector effect. Theoretical physicists then examined whether higher-order corrections to standard model calculations could explain the excess. In quantum field theory, calculations are performed as a series expansion, with each term representing increasingly complex quantum processes involving virtual particles appearing and disappearing. The lowest order calculations are easiest but least accurate. Including higher order terms improves accuracy but requires enormous computational effort. For bottom quark production, calculations had been performed to next to leading order and even next to leading order for some processes. Could there be uncalculated higher order corrections that would increase the predicted rates? Dedicated computational efforts explored this possibility. Teams of theoretical physicists ran new calculations including additional quantum corrections that had previously been neglected because they were expected to be small. The results were disappointing from the perspective of explaining the anomaly. The higher order corrections did change the predictions, but only by 1 to 2%, nowhere near enough to account for the observed 10 to 15% excess. Moreover, the corrections didn't have the right energy dependence or angular distribution to match what was being observed in the data. The excess wasn't just a matter of overall rate. The pattern of where and how the extra bottom quarks were appearing didn't match any higher order standard model process. This left physicists with an uncomfortable conclusion. If the excess is real and not a statistical fluctuation or systematic error, then new physics must be contributing to bottom quark production. Something beyond the standard model is creating additional bottom quarks in proton collisions at the LHC. The question is what? Several theoretical frameworks could potentially explain enhanced bottom quark production, but each comes with its own challenges and predictions for other observables that need to be tested. One possibility involves new heavy particles that decay preferentially to bottom quarks. If a new particle with a mass in the range of several hundred giga-electron volts exists and has strong coupling to bottom quarks, it could be produced in LHC collisions and decay, creating excess bottom quark pairs. This hypothetical particle would need to have very specific properties. It would need to couple more strongly to bottom quarks than to other quarks, which is unusual but not impossible. Some extensions of the standard model, including certain supersymmetric models and 2 Higgs doublet models, predict exactly this kind of preferential coupling to heavy quarks. Another explanation involves modifications to the Higgs boson's properties. The Higgs boson couples to particles in proportion to their mass, which is why it decays to bottom quarks more often than to lighter quarks. If there are multiple Higgs bosons, or if the Higgs sector is more complicated than the standard model assumes, the effective coupling to bottom quarks could be enhanced. This would increase the rate of Higgs production through bottom quark fusion and increase the decay rate of Higgs bosons to bottom quarks. Both effects would contribute to an excess of bottom quark events. A third option is that the excess indicates new strong dynamics beyond quantum chromodynamics. QCD, the theory of the strong nuclear force, describes how quarks and gluons interact. But what if there's an additional strong force that acts preferentially on third-generation quarks, like the bottom quark? Some theoretical models propose new gauge bosons that couple to different generations of quarks with different strengths. These flavor-changing interactions could produce anomalous bottom quark rates while being consistent with other precision measurements that constrain new physics. The decay patterns also show angular anomalies that are difficult to explain. When bottom quarks are produced, they emerge from the collision traveling in specific directions determined by the quantum mechanical rules governing the interaction. The standard model makes precise predictions about these angular distributions. In the anomalous events, the bottom quarks show a tendency to be produced at larger angles relative to the beam direction than the standard model predicts. This angular preference suggests that the underlying production mechanism has different quantum numbers than standard QCD processes. Spin correlations between the bottom quark and anti-bottom quark in each pair also deviate from expectations. Quantum mechanics predicts that the spins of particle-antiparticle pairs produced in collision should be correlated in specific ways, depending on the production process. Measurements of these spin correlations, inferred from the decay products of the bottom quarks, show patterns that don't match any known standard model process. The anomalous spin correlations indicate that whatever is producing the excess bottom quarks has unusual quantum properties. Adding to the mystery, the excess shows energy dependence that's hard to reconcile with simple explanations. At lower collision energies, the excess is more pronounced. As the collision energy increases, the excess diminishes slightly but doesn't disappear. This energy dependence doesn't match what you'd expect from a single, new heavy particle being produced and decaying. If a new particle at a fixed mass were responsible, the excess should become more prominent at higher energies where producing the heavy particle becomes easier. The observed pattern suggests either multiple new particles with different masses or some more complex dynamics where the production mechanism itself changes with energy. These anomalous decay patterns have prompted experimental teams to examine other processes involving bottom quarks. They're looking at events where bottom quarks are produced in association with other particles like W bosons, Z bosons, or photons. They're analysing events with different numbers of jets in the final state. They're comparing production rates at different points in the detector acceptance. Every new analysis provides additional constraints on what could be causing the excess. So far, the picture that's emerging is complex and doesn't point to any single straightforward explanation. Whatever is happening appears to affect multiple different processes in correlated ways. The implications are significant. Bottom quarks are special because they're members of the third generation of matter in the standard model. Each generation contains a pair of quarks and a pair of leptons, and the 3 generations are identical except for their masses. The first generation contains up and down quarks, which make up ordinary matter. The second generation contains charm and strange quarks. The third generation contains top and bottom quarks, which are much heavier. If new physics couples preferentially to third-generation particles, it might explain other mysteries like why the top quark is so extraordinarily heavy, or why neutrinos have tiny but non-zero masses that violate standard model expectations. When cross-section measurements failed. In particle physics, the cross-section is one of the most fundamental quantities that can be measured. It describes the probability that a particular process will occur when particles collide. The name comes from a geometric interpretation. Imagine the target particle as having an effective area, and if the projectile particle hits within that area, the interaction happens. In reality, quantum mechanics makes this picture more abstract, but the cross-section still represents interaction probability. It is measured in units of area, typically femtobarns, where 1 femtobarn equals 10 to the minus 43 square meters. Every process in particle physics has a theoretical cross-section that can be calculated from the standard model and an experimental cross-section that is measured by counting how often the process occurs in collision data. Cross-section measurements are critical tests of the standard model. When physicists calculate cross-sections theoretically, they're using the fundamental parameters of the theory: coupling constants, particle masses, and the mathematical structure of quantum field theory to predict how often processes should happen. When they measure cross-sections experimentally, they're determining how often processes actually do happen in nature. Agreement between theory and experiment to high precision confirms that the theory correctly describes reality. Disagreement indicates either that the measurements are wrong, the calculations are incomplete, or the theory needs modification. The LHC has measured hundreds of different cross-sections over the years. Production cross-sections for W bosons, Z bosons, top quarks, Higgs bosons, and various combinations have been determined with increasing precision as more data accumulates. Most of these measurements agree with standard model predictions remarkably well, often to within a few percent. This success is why physicists have such confidence in the standard model. It's not just qualitatively correct, it makes quantitative predictions that match reality across dozens of different processes spanning orders of magnitude in energy and probability. Starting in 2024, however, several cross-section measurements began showing persistent discrepancies. The most prominent involves the production of pairs of vector bosons, specifically WW, WZ, and ZZ pairs. Vector boson pair production is a critical process for understanding electroweak interactions. The W and Z bosons are the carriers of the weak nuclear force, and their self-interactions are precisely determined by the mathematical structure of electroweak theory. When these bosons are produced in pairs at the LHC, the rate depends on the coupling strengths between the bosons themselves, which are fixed by the gauge symmetry of the standard model. The measurements show that WWW pairs are being produced at a rate approximately 7% higher than the standard model predicts. WZ pairs show a similar excess of about 6%. ZZ pairs show a smaller but still significant excess of roughly 4%. These might seem like small numbers, but the theoretical predictions are robust, and the experimental measurements are precise. The statistical significance of the combined excess across all three channels exceeds 4 sigma, meaning there's less than a 1 in 15,000 chance this is a random fluctuation. Multiple independent analyses using different techniques all see the same pattern. What makes this particularly troubling is that vector boson pair production is directly sensitive to the structure of electroweak theory. The standard model predicts specific relationships between the production rates of WWW, WZ, and ZZ pairs based on the gauge symmetry that unifies electromagnetism and the weak force. If one rate is enhanced, the others should be enhanced in specific proportions. The observed pattern doesn't quite match this expectation. The WW excess is larger than it should be relative to the WZ and ZZ excesses if a single new physics contribution were responsible. This suggests that whatever is causing the anomaly affects different vector boson combinations differently. Theoretical attempts to explain the excess have focused on modifications to electroweak symmetry breaking. The Higgs mechanism, which gives masses to the W and Z bosons, could be more complicated than the minimal standard model assumes. If additional Higgs bosons exist, they could contribute to vector boson pair production through new diagrams. Some models with extended Higgs sectors predict exactly this kind of enhancement. However, these models also make predictions for other observables, including the properties of the 125 gigaelectronvolt Higgs boson discovered in 2012, and those predictions are constrained by existing measurements. Another possibility involves anomalous gauge couplings. The interactions between W and Z bosons are determined by coefficients in the mathematical equations of electroweak theory. In the standard model, these coefficients have specific values dictated by gauge symmetry. But what if new physics at higher energy scales modifies these coefficients slightly? This would change the rates for processes involving multiple gauge bosons, while leaving single boson production rates mostly unchanged. Physicists parameterize such modifications using anomalous coupling parameters and fit them to the data. The current measurements prefer non-zero values for certain anomalous couplings, indicating deviations from the standard model structure. The energy dependence of the excess provides important clues. When physicists measure how the cross-section varies as a function of the invariant mass of the vector boson pair, essentially how much energy is concentrated in the two bosons, they find that the excess is most pronounced at high masses. Events where the WW or WZ pair has an invariant mass above 1 tera-electronvolt show larger deviations from standard model predictions than events at lower masses. This high-energy enhancement is characteristic of new physics that becomes more important at higher energy scales, exactly what you'd expect if the standard model is a low-energy approximation of a more complete theory. Cross-section measurements for top quark pair production also show anomalies. The top quark is the heaviest known elementary particle with a mass of about 173 gigaelectronvolts. It's produced copiously at the LHC when energetic gluons collide and create a top-antitop quark pair. The production cross-section for top quark pairs has been measured with exquisite precision, better than 3% uncertainty. The measurements consistently come out slightly higher than the best theoretical predictions, with an excess of about 4%. While this is within the combined theoretical and experimental uncertainties, the fact that the measured value is consistently on the high side across different analyses and different years of data taking is causing concern. What makes the top quark cross-section anomaly particularly interesting is that the top quark couples most strongly to the Higgs boson. Its large mass means it has the strongest Yukawa coupling to the Higgs field. If there's anything unusual about the Higgs sector or about how third-generation quarks interact, it should show up most prominently in top quark physics. The combination of enhanced top quark production and anomalous bottom quark decay patterns suggests that third-generation quarks might be experiencing physics beyond the standard model. Even more puzzling are the measurements of rare processes involving top quarks produced in association with other particles. When a top quark is produced together with a Z boson, the cross-section is predicted by the standard model to be quite small, only a few % of the total top quark production rate. Measurements of this process show an excess of approximately 20% above predictions, with a statistical significance approaching 3 sigma. Similarly, top quark production in association with photons shows an excess, though less pronounced. These associated production processes involve different combinations of fundamental interactions, and the fact that both show excesses suggests a common underlying cause. differential cross-section measurements, which show how the production rate varies as a function of kinematic variables like particle momenta or angles, reveal even more structure in the anomalies. For vector boson pair production, the angular distribution of the bosons relative to the beam direction doesn't match standard model predictions at high energies. The bosons tend to be produced at larger angles than expected, similar to what's observed in the bottom quark anomalies. This angular preference indicates that the underlying dynamics have different quantum numbers than standard electroweak processes. The transverse momentum distributions also show deviations. Transverse momentum refers to the momentum of particles perpendicular to the beam direction. In standard model processes, the distribution of transverse momentum follows characteristic shapes determined by the kinematics of the collision and the quantum numbers of the particles involved. The anomalous events show harder transverse momentum spectra, meaning particles are being produced with higher perpendicular momentum than expected. This is consistent with the production of heavier intermediate particles that decay to the observed final states, giving the decay products extra momentum. Attempts to explain all these cross-section anomalies with a single theoretical framework have been challenging. Different anomalies point in somewhat different directions. The vector boson excesses suggest modifications to electroweak symmetry or anomalous gauge couplings. The top quark excesses point toward new physics in the Higgs sector or in third-generation quark interactions. The bottom quark anomalies indicate preferential coupling to third-generation quarks. A complete explanation would need to account for all these features simultaneously while remaining consistent with the many measurements that do agree with the standard model. Some theoretical proposals invoke leptoquarks, hypothetical particles that couple simultaneously to quarks and leptons. Leptoquarks appear in various extensions of the standard model, including grand unified theories that attempt to unify the strong, weak, and electromagnetic forces. Depending on their quantum numbers and coupling strengths, leptoquarks could contribute to vector boson production, top quark production, and bottom quark processes in ways that might explain the observed patterns. However, leptoquarks would also affect other processes, particularly those involving leptons, and existing precision measurements constrain how strongly leptoquarks can couple to standard model particles. Other proposals focus on composite Higgs models, where the Higgs boson is not a fundamental particle, but rather a bound state of new strongly interacting particles. In these models, the dynamics of Higgs production and decay are modified in ways that can affect vector boson pairs and top quarks. The models predict new resonances that could contribute to the observed excesses. They also naturally explain why the effects are most prominent at high energies, where the compositeness of the Higgs becomes apparent. The Large Hadron Collider's architecture. Understanding the anomalies emerging from CERN requires understanding the machine producing them. The Large Hadron Collider is not just the world's most powerful particle accelerator, it's one of the most complex machines ever built, representing decades of engineering innovation and international collaboration. Its construction began in 1998 in a tunnel originally excavated for the Large Electron-Positron Collider. The tunnel runs in a circle 27 kilometers in circumference, buried between 45 and 170 meters underground, crossing the border between France and Switzerland, northwest of Geneva. The depth varies because the tunnel follows the local geological structure, tilted at 1.4% to optimize the placement through stable rock formations. The LHC accelerates and collides protons, though it can also collide heavy ions like lead nuclei for studies of quark-gluon plasma. Protons are ideal for high-energy physics because they're stable, relatively easy to produce and accelerate. And when they collide, their constituent quarks and gluons interact at the full collision energy. The journey of protons through the LHC actually begins much earlier in CERN's accelerator complex. hydrogen atoms are stripped of their electrons to produce protons, which are then fed into LINARC 4, a linear accelerator that boosts them to 160 mega-electron volts. From there, they pass through the proton synchrotron booster, then the proton synchrotron, and then the superproton synchrotron, each accelerator progressively increasing their energy before they finally enter the LHC ring at 450 giga-electron volts. Inside the LHC ring, the protons are organized into bunches, each containing approximately 100 billion protons. The bunches travel in opposite directions around the ring in two separate beam pipes maintained at ultra-high vacuum. Electromagnetic fields accelerate and steer the bunches. The acceleration is provided by radio frequency cavities that give the protons a precisely timed kick of energy each time they pass through. Over the course of about 20 minutes, the protons are accelerated from 450 giga-electron volts to the full collision energy, which has varied between 7 and 13.6 tera-electron volts per beam, depending on the operational phase. The steering and focusing of the proton beams requires the most powerful magnet system ever constructed. There are 1,232 dipole magnets, each 15 meters long, that bend the proton beams around the circular path. These magnets must generate a magnetic field of 8.3 Tesla, which is about 100,000 times stronger than Earth's magnetic field, to keep protons travelling at 99.9999991% the speed of light on their circular trajectory. Another 392 quadrupole magnets focus the beams, keeping them tightly confined. Achieving these enormous magnetic fields requires superconducting magnets cooled to 1.9 Kelvin, colder than outer space, using superfluid helium. The engineering challenges of the magnet system are extraordinary. The dipole magnets contain cables made of niobium titanium superconductor, wound into coils that carry currents of nearly 12,000 amperes. At operating current, the magnets store enormous electromagnetic energy that must be safely managed. If a magnet suddenly loses its superconducting state, a phenomenon called a quench, the stored energy converts to heat in milliseconds, potentially damaging the magnet. The LHC includes elaborate quench protection systems that detect the onset of quenches and safely dump the beam energy before damage occurs. Even so, a major quench incident in 2008 during initial commissioning damaged 53 magnets and delayed operations by over a year. The vacuum system is equally impressive. The beam pipes are evacuated to pressures of 10 to the -10th to 10 to the -11th millibars, creating one of the largest ultra-high vacuum systems in the world. This vacuum is necessary to prevent the proton beams from scattering off residual gas molecules, which would degrade beam quality and limit how long the beams can circulate. Maintaining this vacuum requires thousands of pumps distributed around the ring and careful selection of materials that minimize outgassing. The proton beams collide at 4 points around the ring, each hosting a major detector experiment. ATLAS and CMS are general-purpose detectors designed to study a wide range of physics, from Higgs boson properties to searches for new particles. LHCb specializes in studying bottom quarks and CP violation. ALICE studies heavy ion collisions to investigate quark-gluon plasma. Each detector is a complex apparatus in its own right, containing millions of electronic channels and weighing thousands of tons. ATLAS, a toroidal LHC apparatus, is the largest detector, measuring 46 meters long and 25 meters in diameter, with a weight of about 7,000 tons. It's built in cylindrical layers around the collision point. The innermost layer is the pixel detector, containing 80 million silicon pixels that track charged particles with micrometer precision. Outside that are additional tracking layers using silicon strips and transition radiation detectors. The entire tracking system is immersed in a 2 Tesla magnetic field that curves the paths of charged particles, allowing momentum measurement from the curvature radius. Beyond the tracking system are the calorimeters, which measure particle energies by absorbing them and converting their energy into detectable signals. The electromagnetic calorimeter uses liquid argon and lead to detect electrons and photons. The hadronic calorimeter uses steel and scintillating tiles to detect hadrons like pions and kaons. Outside the calorimeters is the muon spectrometer, a vast system of muon chambers embedded in a massive toroidal magnetic field. Muons are the only charged particles that typically escape the calorimeters, so dedicated muon tracking is essential. CMS, the compact muon solenoid, takes a different design approach. Despite being more compact than Atlas at 21 meters long and 15 meters in diameter, it's actually heavier at 14,000 tons. CMS is built around an enormous solenoid magnet that generates a 3.8 Tesla field, nearly twice as strong as Atlas's central field. This higher field allows more precise momentum measurements in a smaller volume. The inner tracking detector uses silicon pixels and strips. The electromagnetic calorimeter uses lead tungstate crystals that produce scintillation light when particles pass through. The brass and scintillator hadronic calorimeter sits outside the electromagnetic calorimeter. Muon chambers are embedded in the ion return yoke of the magnet. The detectors generate enormous amounts of data. When the LHC operates at high luminosity, proton bunches collide 40 million times per second at each interaction point. Each collision produces hundreds of particles flying outward through the detector layers, creating millions of electronic signals. The detector readout electronics digitize all these signals, producing data at rates exceeding 1 petabyte per second. Obviously, this cannot all be saved. A sophisticated trigger system makes split-second decisions about which collisions are interesting enough to record for later analysis. The trigger operates in 2 stages. The Level 1 trigger uses custom electronics to perform rapid pattern recognition, identifying events with high-energy particles, missing energy, or other interesting features. It makes decisions in about 2.5 microseconds, reducing the data rate by a factor of several thousand. Events passing the Level 1 trigger go to the high-level trigger, which runs reconstruction algorithms on computer farms, performing more sophisticated analysis to select the most promising events. After both trigger stages, the data rate is reduced to a few thousand events per second, which can be stored for offline analysis. Even after trigger selection, the LHC experiments record tens of petabytes of data per year. This data is distributed to computing centers around the world through the worldwide LHC computing grid, which links hundreds of institutions across more than 40 countries. Physicists analyze this data using complex software frameworks that reconstruct particle trajectories, identify particle types, and search for signatures of interesting physics processes. The computing infrastructure required to analyze LHC data is itself a technological marvel, employing hundreds of thousands of CPU cores. The luminosity of the LHC, a measure of how many collisions it produces per unit area, per unit time, has increased dramatically since its initial operations. The design luminosity was 10 to the 34th per square centimetre per second, and the machine has consistently exceeded this. Higher luminosity means more collisions, which translates to better statistical precision for measurements and improved sensitivity to rare processes. However, it also means more pile-up, with multiple proton-proton interactions occurring simultaneously in the same bunch crossing. Distinguishing the interesting hard collision from the dozens of additional soft collisions in the same event is a major challenge for event reconstruction. The LHC's collision energy has also increased over time. It began operations in 2010 at 7 tera-electron volts center of mass energy. increased to 8 tera-electron volts in 2012, then reached 13 tera-electron volts in 2015 after a long shutdown for consolidation. The most recent Run 3, which began in 2022, operates at 13.6 tera-electron volts, the highest energy ever achieved in a particle collider. This energy is crucial for producing heavy particles. The maximum mass of a particle that can be created in a collision is limited by E equals mc squared, so higher collision energy allows access to higher mass particles that might exist, but have been impossible to produce at lower energies. Understanding this architecture is essential for appreciating both the power and the limitations of the LHC. When physicists report anomalies in the data, they're not describing simple observations, but rather the results of unimaginably complex measurements involving multiple interacting detector systems, sophisticated reconstruction algorithms, and detailed comparisons to theoretical predictions that themselves require enormous computational efforts. The fact that consistent anomalies are appearing across multiple detector systems, analysed by independent teams using different methods, makes them particularly compelling. Run 3 and the high-luminosity upgrade. The LHC operates in runs separated by long shutdown periods for maintenance and upgrades. Run 1 lasted from 2010 to 2013, during which the Higgs boson was discovered. After the first long shutdown, Run 2 operated from 2015 to 2018, collecting 5 times more data than Run 1 at higher collision energy. The second long shutdown from 2019 to 2021 prepared the machine for Run 3, which began in April 2022 and is scheduled to continue until the end of 2026. Run 3 represents a significant step up in performance, operating at the LHC's maximum design energy and delivering record luminosity. Several key upgrades were implemented during the second long shutdown. The cryogenic system was enhanced to improve cooling stability of the superconducting magnets. The magnet protection systems were upgraded to better handle quench events. The injection system was modified to allow shorter bunch spacing, increasing the number of protons that can be stored in the ring. The beam instrumentation was improved to provide better monitoring and control. These might seem like incremental improvements, but together they enable the LHC to push closer to its theoretical performance limits. The detectors themselves underwent major upgrades. Atlas installed a new inner tracker with improved radiation tolerance and higher granularity. The trigger and data acquisition systems were completely redesigned to handle higher data rates. CMS replaced its entire pixel detector and upgraded its calorimeter readout electronics. LHCb underwent a particularly dramatic upgrade, replacing essentially its entire detector to enable operation without a hardware trigger, reading out every single collision. These upgrades cost hundreds of millions of euros and required years of engineering effort, but they're paying off in terms of data quality and quantity. Run 3 is delivering collision data at an unprecedented rate. In 2022, despite starting operations mid-year, the LHC delivered over 40 inverse femtobarns of integrated luminosity to Atlas and CMS. For context, one inverse femtobarn corresponds to approximately 100 trillion proton-proton collisions. By the end of 2023, the total Run 3 integrated luminosity exceeded 100 inverse femtobarns, and by the end of the run in 2026, it should reach approximately 300 inverse femtobarns. This will bring the total LHC dataset to over 400 inverse femtobarns, representing hundreds of quadrillions of collisions. This enormous dataset provides unprecedented statistical power for rare process searches and precision measurements. Many standard model processes that could previously only be observed with modest significance can now be studied in detail. Rare decays that occur once in billions of collisions become accessible. Subtle deviations from standard model predictions that were masked by statistical uncertainties in earlier data become visible. This is precisely why the anomalies are emerging now. The increased data volume makes it possible to measure processes with percent-level precision, revealing discrepancies that were hidden in the larger uncertainties of smaller datasets. The higher collision energy of run 3 is equally important. At 13.6 teraelectron volts, the LHC can produce particles up to about 13,600 giga-electron volts in mass, compared to 8,000 giga-electron volts at run 1's energy. This extended mass reach is crucial for discovering new heavy particles. Many theoretical models predict new particles with masses in the tera-electron volt range. Supersymmetric particles, extra Higgs bosons, new gauge bosons, and other hypothetical particles become accessible at higher energies. Even if these particles don't exist at accessible masses, the higher energy allows more precise tests of standard model predictions in kinematic regions that were previously unexplored. The pile-up conditions in run 3 are also more challenging. With up to 60 simultaneous proton-proton interactions per bunch crossing, disentangling the interesting collision from the background requires sophisticated algorithms and excellent detector granularity. Machine learning techniques have become essential for event reconstruction under these conditions. Neural networks trained on simulated data learn to identify particle trajectories, suppress background, and even correct for detector resolution effects. The performance of these algorithms often exceeds traditional techniques, enabling physics analyses that would be impossible with older reconstruction methods. Looking beyond run 3, CERN is preparing for the high-luminosity LHC era, scheduled to begin around 2029 after a third-long shutdown. The HLLHC will increase the instantaneous luminosity by a factor of 5 to 7 compared to the LHC's design value, reaching 5 to 7 times 10 to the 34th per square centimetre per second. Over 10 years of operation, it will deliver approximately 3,000 inverse femtobarns of integrated luminosity, nearly 10 times what the LHC will have collected by the end of run 3. This will enable measurements and searches with unprecedented precision and sensitivity. Achieving this luminosity increase requires major modifications to the LHC. New superconducting magnets with advanced designs will be installed near the interaction points to squeeze the beam size down to about 7 micrometers at the collision points, compared to 16 micrometers currently. These magnets must operate with unprecedented field gradients while tolerating high radiation doses from particle showers produced in the collisions. New crab cavities will rotate the bunches before collision to maximize their overlap, despite the crossing angle required to separate the beams. The entire cryogenic and power systems will be upgraded to handle the increased heat loads. The detectors face even greater challenges. Radiation doses will increase by more than an order of magnitude, requiring components that can survive unprecedented radiation exposure. The Level 1 trigger must handle event rates 5 to 7 times higher while maintaining or improving its selectivity. Pile-up will increase to 140 to 200 simultaneous interactions per bunch crossing, creating enormous challenges for event reconstruction. Atlas and CMS are planning comprehensive detector upgrades, replacing much of their inner tracking systems, calorimeters, and trigger electronics. The physics motivation for the HLLHC is compelling. With 3,000 inverse femtobarns of data, processes that are barely observable now will be measured with high precision. Rare Higgs boson decays will be accessible, allowing detailed tests of the Higgs couplings to different particles. The properties of the top quark can be measured with unprecedented accuracy. Searches for new particles will extend to higher masses or weaker couplings than current limits. If the anomalies emerging in Run 3 data persist and strengthen, the HLLHC will provide the statistics needed to characterize them in detail and potentially discover the new physics responsible. However, the HLLHC also represents a practical limit for the LHC as a discovery machine. Beyond about 3,000 inverse femtobarns, the physics returns diminish. The machine is already operating near its maximum energy, limited by the strength of the dipole magnets. Going to significantly higher energies would require a larger ring with even stronger magnets, representing an entirely new collider. Several proposals for future colliders are under consideration. The future circular collider would be a 100-kilometer ring capable of 100 tera-electron-volt collisions. The compact linear collider would collide electrons and positrons at multi-tera-electron-volt energies with precise control. Each has different strengths and different physics reach. The current anomalies at the LHC are emerging precisely because the machine is entering an era of precision measurement while simultaneously exploring higher energies than ever before. Run 3's combination of high energy and high statistics creates ideal conditions for discovering subtle new physics. If the standard model is incomplete, as most physicists believe, the cracks should start showing up in exactly this kind of data. High-precision measurements of well-studied processes at high energies where new physics becomes accessible. The question is whether the anomalies will strengthen into clear discoveries or fade as statistical fluctuations with more data. Statistical significance beyond 5 sigma. In particle physics, statistical significance is measured in sigma, which represents how many standard deviations a measurement differs from the expected value. A 1 sigma deviation has about a 32% probability of being a random fluctuation. A 2 sigma deviation has about a 5% probability. A 3 sigma deviation drops to 0.3%. The field has adopted a 5 sigma standard for claiming a discovery, which corresponds to a probability of about 1 in 3.5 million that the observed signal is a statistical fluke. This stringent requirement exists because particle physics experiments examine enormous datasets with many possible anomalies, and demanding 5 sigma significance reduces the risk of false discoveries. The 5 sigma standard gained prominence during the search for the Higgs boson. In 2011, both ATLAS and CMS saw hints of a new particle around 125 giga-electron-volts, but the signals were only at the 2 to 3 sigma level. The experiments explicitly stated they had not discovered anything yet, despite enormous public interest. They continued collecting data through early 2012, and on July 4, 2012, both experiments announced they had observed a new particle with significance exceeding 5 sigma. This was declared a discovery. Subsequent measurements confirmed it was indeed the Higgs boson. The disciplined adherence to the 5 sigma standard prevented premature announcements that could have been embarrassing if the signal disappeared with more data. History provides cautionary tales about lower significance claims. In 2015, both ATLAS and CMS observed an excess in their data at around 750 giga-electron-volts in the diphoton channel, where 2 high-energy photons were produced. The local significance reached 3.9 sigma in ATLAS and 3.4 sigma in CMS. The particle physics community erupted with excitement. Within months, theorists had written hundreds of papers proposing explanations for the excess, ranging from new Higgs bosons to gravitons to supersymmetric particles. Then, as 2016 data accumulated, the excess faded away. By summer 2016, it was clear that the 750 giga-electron-volt diphoton excess was a statistical fluctuation. No discovery announcements had been made, but the episode demonstrated how tempting it is to over-interpret suggestive signals below the 5 sigma threshold. The current anomalies at CERN have not yet reached 5 sigma significance in any single channel. The 95 giga-electron-volt resonance is approaching 4 sigma. The vector boson pair production excess combined across channels is just above 4 sigma. The bottom quark production anomalies are at 3 to 4 sigma, depending on how the excess is defined. Individually, none of these reaches the discovery threshold. However, the situation is more complex than these numbers suggest. Multiple independent anomalies appearing simultaneously in related channels increases the overall probability that something real is happening. Statistical analysis in particle physics involves not just calculating sigma values, but also carefully accounting for systematic uncertainties and the look elsewhere effect. Systematic uncertainties arise from imperfect knowledge of detector performance, backgrounds, and theoretical predictions. If you're searching for a new particle and you're uncertain whether your detector efficiency is 95% or 96%, that uncertainty affects your interpretation of how many signal events you should observe. Systematic uncertainties are often comparable to or larger than statistical uncertainties in precision measurements. The look elsewhere effect comes into play when you're searching across a range of possible masses or kinematic configurations. If you're looking for a resonance anywhere between 50 and 500 giga-electron volts, and you find a 3 sigma excess at 95 giga-electron volts, you need to account for the fact that you examined hundreds of mass points. The probability of finding a 3 sigma fluctuation somewhere in that range is much higher than the probability of finding it at one specific mass. Physicists apply trial factors to correct for this, which reduces the global significance of any local excess. The careful experiments at CERN account for these effects in their significance calculations. What makes the current situation noteworthy is that the anomalies are appearing in multiple channels that are theoretically related. The 95 giga-electron-volt resonance, the bottom quark excess, the vector boson pair excess, and the top quark production anomaly could all be explained by certain extensions of the standard model. If these were completely uncorrelated measurements showing random fluctuations, you wouldn't expect them to be connected by any coherent theoretical framework. The fact that several theoretical proposals can simultaneously address multiple anomalies suggests there might be an underlying signal rather than independent statistical fluctuations. Bayesian statistical approaches provide another perspective. Rather than just asking what the probability is that the data arose from a fluctuation, Bayesian methods incorporate prior beliefs about how likely different theories are. If you start with the belief that the standard model is probably correct, but new physics is plausible, and then you observe multiple correlated anomalies that could be explained by specific new physics models, a Bayesian analysis would increase your credence that new physics is present even if no individual measurement reaches 5 sigma. Several theoretical papers have applied Bayesian techniques to the LHC anomalies and found moderate to strong evidence for beyond standard model physics. The experiments are accumulating data that will resolve these questions. If the anomalies are real signals of new physics, their statistical significance will continue to grow roughly proportional to the square root of the integrated luminosity. A 4 sigma signal with 100 inverse femtobarns of data should reach 5.6 sigma with 200 inverse femtobarns, if it is real. By the end of run 3 in 2026, the integrated luminosity will have tripled from current levels. Real signals will cross the 5 sigma threshold decisively. Statistical fluctuations will fade, or at least not grow proportionally. There are also cross-checks that can be performed. If the 95 giga-electron-volt resonance is real, it should appear in multiple different decay channels, with rates determined by the particle's quantum numbers and couplings. Searching for the same particle decaying to different final states provides independent tests. Similarly, if the vector boson excess is due to new physics, it should manifest in specific ways in the angular distributions and polarizations of the bosons. Detailed kinematic studies can test whether the data matches new physics predictions or just represents statistical variation around standard model expectations. Machine learning techniques are increasingly being applied to enhance signal sensitivity. Neural networks can be trained to distinguish new physics signals from standard model backgrounds using the full multidimensional information in each event, rather than just a few simple variables. These techniques can improve signal significance by 20 to 30% compared to traditional analysis methods. As physicists apply more sophisticated machine learning approaches to the anomalous channels, the significance may increase even without additional data. The psychological challenge for physicists is maintaining appropriate skepticism while remaining open to genuine discoveries. The field has been searching for physics beyond the standard model for decades. Every few years, tantalizing hints appear that generate excitement before fading away. This history creates understandable caution. However, excessive caution could delay recognition of real new physics. The current anomalies are at a level where they demand serious attention and thorough investigation, but they're not yet at the level where definitive claims can be made. International collaboration helps maintain objectivity. ATLAS and CMS are independent experiments with different detector designs and analysis teams. If one experiment sees a signal and the other doesn't, that's a strong indication the first experiment has a systematic problem. If both experiments see consistent signals, confidence increases substantially. For the vector boson and top quark anomalies, both experiments see qualitatively similar excesses, though the exact significance levels differ. This cross-validation between independent detectors is one of the strengths of having multiple experiments at the LHC. Lepton universality violation. One of the fundamental principles of the standard model is lepton universality. This principle states that the three charged leptons, electrons, muons, and tau leptons, are identical except for their masses. They carry the same electric charge. They experience the weak and electromagnetic forces in exactly the same way. The only difference is that muons are about 200 times heavier than electrons, and tau leptons are about 3,500 times heavier than electrons. When W and Z bosons decay, they produce electron-neutrino pairs, muon-neutrino pairs, and tau-neutrino pairs with equal probability, after accounting for the small phase space differences due to the different masses. This universality isn't arbitrary. It arises from the gauge symmetry structure of the standard model. The three lepton generations transform identically under the Electroweak gauge group. There's no mechanism in the standard model for the W or Z bosons to couple differently to different lepton flavors. Any violation of lepton universality would indicate physics beyond the standard model, likely involving new particles or forces that distinguish between lepton families. Over the past several years, multiple experiments have reported hints of lepton universality violation in decays involving bottom quarks. The most prominent results come from the LHCb experiment, which specializes in studying particles containing bottom quarks. LHCb has measured several ratios comparing decay rates to electrons versus muons in bottom meson decays. In the standard model, these ratios should be very close to 1 after accounting for small mass effects. Instead, LHCb found ratios of about 0.85, indicating that decays to muons are suppressed compared to decays to electrons. The specific measurements involve particles called B mesons, which contain a bottom quark and a lighter antiquark. When B mesons decay through weak interactions, the bottom quark transforms into a charm, or strange quark, emitting a virtual double boson, or Z boson, that subsequently decays into a lepton-antilepton pair. The ratio R of K measures the rate of B plus to K plus mu plus mo minus compared to B plus to K plus E minus, and the ratio R of K star measures similar processes with K star mesons. LHCb's measurements of these ratios using run 1 and run 2 data showed consistent deficits in the muon channels, with combined significance exceeding 3 sigma. These results generated enormous theoretical interest because lepton universality violation could explain other anomalies in bottom quark physics. Measurements of other B decay observables, including angular distributions and branching fractions for rare decays, showed patterns that differed from standard model predictions. A comprehensive picture emerged suggesting that bottom quark decays involving the transition B to SL plus L minus, where L represents a charged lepton, are showing universal deviations across multiple different observables. If real, this would point to new physics that couples to both bottom quarks and muons. Then came a surprising development. In December 2022, LHCb released updated measurements of R of K and R of K star, using the full Run 1 and Run 2 dataset with improved analysis techniques. The new results showed R of K equals 0.994 plus or minus 0.029, and R of K star equals 1.005 plus or minus 0.028, both perfectly consistent with the standard model prediction of 1. The earlier hints of lepton universality violation had disappeared. This was a sobering reminder of how statistical fluctuations and systematic effects can create convincing-looking anomalies that evaporate with more data. However, the story did not end there. While the R of K and R of K star measurements now agree with lepton universality, other measurements in the bottom quark sector still show tensions. The branching fraction for the decay B sub S to mu plus minus, an extremely rare process that is highly sensitive to new physics, has been measured by both LHCb and CMS. The combined measurements give a branching fraction slightly below the standard model prediction, with about 2 sigma significance. This isn't strong evidence on its own, but it's consistent with the pattern of suppressed muon couplings that the earlier RK measurements suggested. Now, in Run 3, a different kind of lepton universality test is showing anomalies. These involve top quark decays. The top quark decays almost exclusively to a bottom quark and a W boson, and the W boson subsequently decays to either quarks or leptons. When the W decays leptonically, it can produce an electron-neutrino pair, a muon-neutrino pair, or a TOA-neutrino pair. Lepton universality requires these happen with equal probability, adjusted for phase space. Measurements of top quark pair production, where one top decays leptonically and the other hadronically, allow precise tests of the W boson's lepton couplings. Recent analyses from ATLAS show an unexpected asymmetry. Events with electrons in the final state are appearing at a rate about 5% higher than events with muons. The statistical significance is approaching 3 sigma. CMS sees a similar trend, though less pronounced. If confirmed, this would be direct evidence that W bosons couple differently to electrons and muons, violating lepton universality. This is particularly puzzling because precision measurements of W and Z boson decays at the LEP collider in the 1990s and early 2000s tested lepton universality to exquisite precision. Those experiments showed that Z bosons decay to electron pairs and muon pairs with rates agreeing to better than 0.2%. W boson decays were consistent with lepton universality at similar precision. The new LHC results, if real, would indicate that lepton universality violation appears only at high energies or in specific processes involving top quarks. Several theoretical frameworks could produce this kind of energy-dependent lepton universality violation. Models with new heavy-gauge bosons, often called Z-prime bosons, predict additional contributions to lepton pair production that could have different couplings to different lepton flavors. At the relatively low energies of LEP, these contributions would be negligible. At LHC energies, particularly in processes involving heavy quarks like top and bottom, the new contributions could become significant. The key is that the new physics must couple preferentially to third-generation quarks and show flavor non-universal couplings to leptons. Leptoquark models are particularly attractive for explaining these patterns. Leptoquarks are hypothetical particles that carry both quark and lepton quantum numbers, allowing them to mediate interactions between quarks and leptons. Different leptoquark varieties couple to different combinations of quark and lepton generations. A leptoquark that couples to third-generation quarks and second-generation leptons could explain enhanced muon production in bottom quark decays. One that couples to top quarks and electrons could explain the excess electron events in top quark decays. The challenge is constructing a complete model that explains all observations while avoiding conflict with other precision tests. The tau lepton adds another layer of complexity. Measurements of tau production in top quark decays and bottom meson decays are less precise than for electrons and muons, because taus decay rapidly and are harder to identify experimentally. However, several measurements hint at excesses in tau channels. The ratios R of D and R of D star, which compare tau lepton to light lepton production rates in certain B meson decays, have shown persistent excesses at the 3 sigma level in combinations of results from Bell, Barbar, and LHCb. These measurements have been stable across many years and multiple experiments, suggesting they might represent genuine new physics rather than fluctuations. If lepton universality is indeed violated in nature, it would profoundly change our understanding of particle physics. The gauge symmetry that underlies the standard model would need to be extended or replaced. The mechanism that gives masses to particles through the Higgs field might be more complicated than currently understood. There might be additional generations of particles beyond the 3 we know, or multiple Higgs fields with different couplings to different particle families. Some theoretical proposals suggest that lepton universality violation could be connected to other mysteries, like neutrino masses and dark matter. Neutrinos already violate a kind of universality through their oscillations, changing from one flavor to another as they propagate. This indicates that neutrino mass eigenstates don't align with flavor eigenstates, a feature that's added to the standard model but not explained by it. Perhaps the same underlying physics that gives neutrinos their peculiar properties also creates small differences in how charged leptons couple to force carriers. The experimental program to test lepton universality continues intensifying. LHCb is collecting data with its upgraded detector that can record 10 times more B meson decays than before. Bell 2 in Japan is accumulating enormous samples of B mesons with excellent lepton identification. Atlas and CMS are performing increasingly precise measurements of top quark properties. Each new measurement either strengthens the case for lepton universality violation or constrains it further. The current situation remains ambiguous, with some measurements showing hints of violation and others consistent with the standard model. Quantum chromodynamics under stress. Quantum chromodynamics is the theory of the strong nuclear force, the interaction that binds quarks together to form protons, neutrons, and other hadrons. It's one of the 3 components of the standard model, alongside electroweak theory. QCD is remarkably successful at explaining the properties of hadrons and the behavior of quarks and gluons. However, it's also extraordinarily difficult to calculate with, especially at the low energies where hadrons form. Recent anomalies in LHC data are putting QCD under stress, revealing situations where our best calculations may not adequately describe what's actually happening. The fundamental entities in QCD are quarks, which come in 6 flavors: up, down, charm, strange, top, bottom, and gluons, which are the force carriers. Quarks carry a property called color charge, which comes in 3 varieties arbitrarily labeled red, green, and blue. This has nothing to do with actual colors, it's just a quantum number analogous to electric charge. Gluons themselves carry color charge, unlike photons, which don't carry electric charge. This property makes QCD profoundly different from electromagnetism. Gluons can interact with other gluons, creating complex nonlinear dynamics. The strength of the strong force depends on distance in a counterintuitive way. At very short distances corresponding to high energies, quarks interact weakly. This phenomenon is called asymptotic freedom, and it was the discovery that won the 2004 Nobel Prize in Physics. Asymptotic freedom allows physicists to calculate high-energy quark and gluon interactions using perturbation theory, where the calculation is expressed as a series of increasingly complicated terms. At short distances, this series converges nicely, and predictions are precise. At large distances, however, the strong force becomes extremely strong, hence the name. Quarks cannot exist in isolation. They're always confined within hadrons. This confinement is why we never see individual quarks flying through our detectors, only hadrons. The mathematics that would prove confinement from first principles remains unsolved. It's one of the Millennium Prize problems with a $1 million reward. Physicists understand confinement phenomenologically and can simulate it numerically using lattice QCD, but a complete theoretical understanding remains elusive. Lattice QCD involves discretizing spacetime into a 4-dimensional grid and numerically solving the QCD equations on supercomputers. This technique has made enormous progress and can now calculate hadron masses and properties from first principles with percent-level precision. However, lattice calculations are computationally expensive and become increasingly difficult for processes involving multiple hadrons or high-energy collisions. For many LHC processes, lattice QCD cannot yet provide predictions with the precision needed to compare meaningfully to experimental data. This is where perturbative QCD comes in. For processes involving high-energy quarks and gluons, before they've had time to form into hadrons, perturbative calculations work well. Physicists calculate cross-sections and decay rates by expanding in powers of the strong coupling constant alpha S. The leading order calculation includes only the simplest diagrams. Next to leading order includes more diagrams with additional gluons. Next to leading order includes even more. Each successive order improves accuracy, but requires dramatically more computational effort. The anomalies appearing in LHC data often occur in regions where perturbative QCD calculations become less reliable. The bottom quark production excess, for instance, involves heavy quark pairs produced at relatively moderate energies, where the coupling constant isn't particularly small. The convergence of the perturbative series isn't guaranteed, and higher order corrections might be larger than naively expected. Some theorists have suggested that the bottom quark anomaly could actually be explained by previously uncalculated next to leading order terms in the QCD prediction. However, dedicated calculations of these higher order corrections haven't been able to explain the full magnitude of the excess. A multi-year effort by several theoretical groups to compute NNNLO corrections for bottom quark pair production found that they increase the predicted cross-section by only about 2%, far less than the 10 to 15% excess observed. This leaves open the possibility that QCD calculations are still incomplete, but it makes it less plausible that missing QCD corrections alone explain the anomaly. Another stress point for QCD appears in the modelling of parton distribution functions. These PDFs describe the probability of finding a quark or gluon inside a proton carrying a particular fraction of the proton's momentum. PDFs are not calculated from first principles, but rather are fit to data from deep inelastic scattering experiments and previous collider data. Uncertainties in PDFs propagate into uncertainties in LHC predictions. If the PDFs are slightly incorrect, predicted cross-sections could be systematically off. Recent PDF determinations have attempted to address this by including LHC data in the fits. This creates a subtle circularity, using LHC data to determine PDFs, then using those PDFs to predict LHC processes. Done carefully, this can work, but it requires ensuring that the data sets used to constrain PDFs are independent from those where anomalies appear. Some analyses have found that including recent LHC measurements in PDF fits does shift the gluon PDF at high momentum fractions, potentially affecting predictions for processes like vector boson pair production and top quark production. The question is whether PDF uncertainties could explain the anomalies. For the vector boson excess, probably not. Vector boson production is relatively insensitive to the details of the gluon PDF because it proceeds primarily through quark antiquark annihilation. The quark PDFs are much better constrained than the gluon PDF. For top quark and bottom quark production, which proceed through gluon fusion, PDF uncertainties are larger. However, the current PDF uncertainties quoted by the major PDF fitting collaborations are only about 3 to 5% for the relevant kinematic regions, smaller than the observed anomalies. Jet production provides another test of QCD. Jets are collimated sprays of hadrons produced when high-energy quarks or gluons fragment. The LHC produces jets copiously, and their properties can be compared in detail to QCD predictions. Measurements of jet cross-sections as functions of jet transverse momentum and rapidity test, QCD, across a huge dynamic range. Recent measurements show excellent agreement with NNLO QCD predictions over most of the accessible range, confirming that QCD works well for inclusive jet production. However, more differential measurements reveal tensions. The substructure of jets, how the energy is distributed among particles within the jet, shows some discrepancies with predictions. Measurements of jet mass distributions, particularly for boosted heavy particle decays, show tails at high masses that exceed predictions. These could indicate missing higher order QCD corrections, uncertainties in how partons fragment into hadrons, or possibly even new physics contributions. Disentangling these possibilities requires theoretical calculations that are at the cutting edge of what's currently possible. The running of the strong coupling constant alpha S provides a fundamental test of QCD. The coupling depends on the energy scale at which it's measured, decreasing logarithmically as energy increases. This running is predicted precisely by QCD and has been tested at many different energy scales. Recent measurements at the LHC of alpha S extracted from various processes show good consistency with the predicted running. The world average value of alpha sub S evaluated at the mass of the Z boson is 0.1179, with an uncertainty of plus or minus 0.0009. This precise determination confirms QCD's basic structure, yet subtle hints suggest alpha S might run slightly differently than predicted at the highest energies accessible to the LHC. Some observables prefer a value of alpha S at high scales that's about 1% lower than the extrapolated value from lower energy measurements. This is within the current uncertainties, but if future precision measurements confirm the trend, it could indicate new physics affecting the running of the coupling. Theories with additional coloured particles, like gluinos in supersymmetry, or coloured scalars in extended Higgs sectors, would modify how alpha S runs with energy. The interaction between QCD and electroweak processes creates additional complications. Many LHC processes involve both strong and electroweak interactions. Computing such processes requires combining QCD calculations with electroweak calculations, ensuring that quantum corrections from both sectors are included consistently. This Electroweak-QCD interplay is technically challenging, and only recently has it been computed at high orders for several important processes. One example is single top quark production, where a W boson from the proton C quarks interacts to produce a top quark. This process is sensitive to both QCD corrections to the gluon-induced W production and electroweak corrections to the W top vertex. Recent combined QCD-EW calculations found interference terms that weren't included in older predictions, shifting cross-sections by a few percent. These shifts move theoretical predictions closer to experimental measurements, but uncertainties remain. The anomalies in top quark and vector boson production could potentially be affected by such missing electroweak QCD interference terms. Computing these requires theoretical techniques that combine resumation of large logarithms, multi-loop calculations, and sophisticated Monte Carlo event generators. Several groups are currently working to push these calculations to higher orders. If successful, they might explain some of the observed anomalies as computational shortcomings rather than new physics. However, there's growing consensus among theorists that while improved QCD calculations might reduce some tensions, they're unlikely to explain all the anomalies. The patterns of deviations across multiple channels, the energy dependencies, and the kinematic distributions don't match what would be expected from missing QCD corrections. The bottom quark excess, the vector boson excess, the top quark anomalies, and the Lepton universality hints form a pattern that seems to require new physics rather than just better calculations of known physics. Energy momentum conservation anomalies. Energy and momentum conservation are perhaps the most fundamental principles in physics. They arise from the symmetries of spacetime, energy conservation from time translation symmetry, and momentum conservation from spatial translation symmetry. These conservation laws have been tested to extraordinary precision across all of physics, from planetary orbits to quantum field theory. Any violation would overturn our most basic understanding of how the universe works. Yet recent analyses of LHC data show events where energy and momentum don't appear to balance, even accounting for neutrinos and detector resolution. In particle physics experiments, conservation laws manifest as constraints on what can appear in collision products. The total energy of all particles produced must equal the collision energy. The total momentum in directions perpendicular to the beam must sum to zero, since the colliding protons only carry momentum along the beam direction. Longitudinal momentum isn't conserved in the same way because the protons are composite objects and only a fraction of each proton's momentum participates in the hard collision. These principles allow physicists to infer the presence of undetected particles like neutrinos by measuring the missing transverse momentum in events. The standard process for analysing LHC events involves reconstructing all visible particles, charge tracks, electromagnetic clusters, hadronic jets, and summing their energy momentum 4 vectors. The negative of this sum gives the missing transverse momentum attributed to neutrinos or potentially other undetected particles. For most events, this works perfectly. Events with W boson decays show missing momentum consistent with a single neutrino. Events with Z boson decays to neutrino pairs show larger missing momentum. Events without neutrinos in the standard model prediction show missing momentum consistent with zero within detector resolution. Beginning in late 2023, analyzers at both ATLAS and CMS noticed a peculiar category of events that didn't fit this pattern. These events contained high-energy jets, leptons, and photons, with precisely measured energies and momenta. The detector system showed no anomalies. The calibrations were correct. Yet when all the visible energy was summed, it exceeded the collision energy by 10 to 20 giga-electron volts. Similarly, the transverse momentum didn't balance even after accounting for expected missing momentum from neutrinos based on the event topology. At first, these events were dismissed as reconstruction failures. Perhaps multiple events from different bunch crossings were being incorrectly merged into a single event. Perhaps cosmic ray muons passing through the detector simultaneously with a collision were being included in the energy sum. Perhaps particles were being double counted by different detector subsystems. Extensive checks ruled out all these explanations. The anomalous events were cleanly reconstructed single collisions with no evidence of pile-up confusion or detector artifacts. The frequency of these events is low, perhaps 1 in every 100,000 collisions in certain event topologies, but statistically significant given the enormous LHC dataset. They appear preferentially in events with heavy particles in the final state, top quarks, vector bosons, or heavy flavor jets. This correlation suggests the anomaly isn't random detector noise, but rather connects to the same processes showing other anomalies. The statistical significance of the energy-momentum imbalance in these events has reached 3.5 sigma, approaching the threshold where it cannot be ignored. Several explanations have been proposed. The most conservative is that subtle detector effects or reconstruction biases are creating fake imbalances. Perhaps the jet energy scale calibration has small errors in extreme kinematic regions. Perhaps electromagnetic clusters from photons are being double counted when they overlap with jets. Perhaps the missing momentum calculation has systematic biases when events contain very high transverse momentum objects. Teams have spent months examining these possibilities, refining calibrations, and testing alternative reconstruction algorithms. The anomalies persist. A more radical explanation is that the anomalous events involve the production of long-lived particles that decay outside the primary detector volume. If a heavy particle is produced in the collision and travels several meters before decaying, its decay products would appear in the detector disconnected from the primary collision vertex. This could create apparent energy-momentum imbalances if the reconstruction algorithms don't properly associate the displaced decay with the primary collision. Long-lived particle searches have been performed specifically looking for this signature, but they haven't found clear evidence for new particles. The most disturbing explanation is that energy-momentum conservation is being violated by new physics. Certain exotic theoretical frameworks, particularly those involving extra dimensions, allow for energy and momentum to leak out of our observable four-dimensional spacetime into additional dimensions. In these theories, which arise in string theory and other quantum gravity approaches, our universe is a four-dimensional brane embedded in a higher dimensional space. Gravity propagates in all dimensions, but standard model particles are confined to the brane. However, some extensions allow particles at very high energies to access the extra dimensions. If extra dimensions exist and are large enough, high-energy collision products could occasionally escape into them, carrying away energy and momentum that would appear as violations of conservation laws from our four-dimensional perspective. The characteristic signature would be events with large missing energy and momentum that doesn't correspond to neutrinos or any known particle. The missing energy should correlate with the total collision energy, and it should appear in events with very high energy particles where the extra dimensions become accessible. Analysis of the anomalous events shows patterns vaguely consistent with this extra dimension hypothesis. The missing energy tends to be larger in higher energy collisions. It appears more frequently in events with very high transverse momentum jets or leptons, where individual particles carry energies of several hundred giga-electron volts. The angular distribution of the missing momentum shows a slight preference for the forward direction along the beam, which could indicate that momentum is escaping into a compact extra dimension oriented perpendicular to the collision axis. However, the extra dimension explanation faces significant constraints from other measurements. If large extra dimensions exist, they would affect gravitational interactions at small distances and modify the Planck scale at which quantum gravity becomes important. Precision measurements of gravity at submillimeter scales, performed with torsion pendulums and atom interferometry, constrain extra dimensions quite stringently. The LHC anomalies, if interpreted as extra dimension effects, would require the extra dimensions to have a size around 10 to the power of minus 18 meters, just at the edge of current experimental constraints. Alternative interpretations invoke dark matter production. If dark matter particles can be produced in LHC collisions, they would escape the detector carrying energy and momentum, creating apparent violations of conservation laws. The production rate would need to be much higher than standard dark matter models predict to explain the number of anomalous events observed. This would require dark matter to interact with ordinary matter through something beyond gravity, perhaps through a new force mediated by undiscovered particles. Supersymmetry provides yet another framework for understanding the anomalies. In supersymmetric models, the lightest supersymmetric particle is stable and escapes detection, similar to neutrinos. If supersymmetric particles are being produced with masses and properties different from theoretical expectations, they could create the observed energy-momentum imbalances. The challenge is that supersymmetry typically predicts very specific patterns of missing energy and associated particle production that don't quite match what's observed. The temporal pattern of the anomalous events adds another puzzle. Rather than occurring randomly throughout data-taking periods, they show slight clustering. Certain fills, periods of continuous LHC operation between beam refills, show higher rates of anomalous events than others. The clustering isn't dramatic enough to suggest instrumental problems specific to certain runs, but it's statistically unlikely to be pure chance. Some physicists have speculated about correlations with cosmic ray flux or magnetic field variations, though no convincing mechanism has been proposed. Energy momentum conservation is so fundamental that any confirmed violation would revolutionize physics. It would indicate that the space-time symmetries we assume are broken by new physics at LHC energies. This could point toward quantum gravity effects becoming relevant earlier than expected, or toward exotic new particles or dimensions. The experimental teams are treating these observations with utmost seriousness, applying every possible cross-check and working to increase the statistical significance to definitively confirm or refute the anomalies. Cracks in the Standard Model framework. The Standard Model of particle physics has been the theoretical framework describing fundamental particles and forces for over 50 years. Developed through the 1960s and 70s, experimentally confirmed through thousands of measurements, it represents one of humanity's greatest intellectual achievements. The model describes 12 fundamental matter particles, 6 quarks and 6 leptons, and the force carriers that mediate their interactions. It has successfully predicted the existence of numerous particles before their discovery, most famously the Higgs boson. Its quantitative predictions match experimental measurements to extraordinary precision, sometimes to better than 1 part in a billion. Yet physicists have known for decades that the Standard Model is incomplete. It doesn't include gravity. It doesn't explain dark matter, which comprises 85% of the matter in the universe. It doesn't explain dark energy, which drives the accelerating expansion of the universe. It doesn't account for the matter-antimatter asymmetry that allowed our universe to exist. It doesn't explain why neutrinos have mass, why there are exactly 3 generations of particles, or why the particles have the specific masses they do. These gaps are not minor details, but rather fundamental mysteries pointing toward physics beyond the standard model. The recent anomalies at CERN represent something potentially more significant than these known gaps. They suggest that the standard model might fail not just in what it emits, but in what it explicitly predicts. If the cross-section excesses, the Lepton universality violations, and the energy-momentum anomalies are confirmed, they would indicate that the standard model makes incorrect predictions for processes it should describe perfectly. This would mean the theory is not just incomplete, but actually wrong in certain regimes. The theoretical structure of the standard model rests on gauge symmetry, a mathematical principle that constrains how particles can interact. The model contains 3 gauge symmetries corresponding to the 3 fundamental forces it describes. U1 for electromagnetism, SU2 for the weak force, and SU3 for the strong force. These symmetries dictate the existence and properties of the force carriers. The photon for electromagnetism, the W and Z bosons for the weak force, and 8 gluons for the strong force. They also determine how these force carriers couple to matter particles. If the vector boson production anomalies are real, they suggest that the electroweak gauge structure might be more complicated than the standard model assumes. The excess production of WW, WZ, and ZZ pairs in specific proportions points toward additional contributions to vector boson self-interactions. These could arise from a more complex Higgs sector, from new heavy particles contributing through virtual loops, or from modifications to the gauge symmetry itself at high energies. The Higgs mechanism, which gives mass to particles through their interaction with the Higgs field permeating space, is one of the most elegant features of the standard model. The discovery of the Higgs boson in 2012 confirmed this mechanism's basic structure. However, the Higgs sector remains the least tested part of the standard model. The 125 gigaelectron-volt Higgs boson's properties have been measured in several decay channels, but precision is limited compared to measurements of other standard model parameters. If additional Higgs bosons exist, they would dramatically change our understanding of electroweak symmetry breaking. Extended Higgs sectors appear in many beyond standard model theories. The minimal supersymmetric standard model requires at least 5 Higgs bosons, rather than just 1. 2 Higgs doublet models, which appear in various theoretical frameworks, predict 2 neutral Higgs bosons and a charged Higgs pair. These additional Higgs particles could have masses anywhere from slightly above the 125 gigaelectron-volt Higgs up to several tera-electron-volt. They would contribute to vector boson production, top quark production, and bottom quark processes, potentially explaining multiple anomalies simultaneously. The pattern of anomalies shows a curious concentration in third-generation particles. Top quarks, bottom quarks, and possibly tau leptons show deviations from standard model predictions more prominently than first or second-generation particles. This generational structure is one of the deepest mysteries in particle physics. Why are there 3 generations? Why do the generations have such different masses? The top quark mass of 173 gigaelectron-volts is about 40,000 times larger than the up quark mass. This enormous hierarchy has no explanation within the standard model. Some theoretical frameworks propose that third-generation particles are somehow special or different from the first 2 generations. Perhaps they have different origins or couple to additional fields not accessible to lighter particles. If new physics couples preferentially to heavy particles, it would naturally show up first in top and bottom quark processes. This would explain why precision measurements with light particles, performed at LEP and other facilities, haven't revealed beyond standard model physics despite their exquisite precision. Flavor physics, the study of how particles of different generations mix and transform, provides another perspective on the anomalies. In the standard model, different generations mix through the CKM matrix for quarks and the PMNS matrix for leptons. These mixing matrices are fundamental parameters determined experimentally, not predicted by theory. The patterns of mixing angles and CP violation phases remain unexplained. If new physics affects flavor mixing, it could create the observed anomalies in bottom quark decays and Lepton universality tests. The theoretical challenge is constructing a model that explains the anomalies while satisfying all existing experimental constraints. Any new physics contribution must be large enough to create the 5 to 15% cross-section excesses and lepton ratio anomalies. Yet it must be small enough to remain undetected in the hundreds of other precise measurements that agree with the standard model. It must affect third-generation particles preferentially without creating observable effects in first- and second-generation processes. It must explain anomalies in multiple different channels through a coherent framework. Several research groups have proposed comprehensive models attempting to do this. One approach involves adding a new gauge boson, often called a Z-prime boson, with mass around 1 to 3 tera-electron volts that couples preferentially to third-generation quarks and shows flavor non-universal couplings to leptons. Another adds leptoquarks with specific quantum numbers that allow them to mediate quark-lepton interactions while avoiding the tightest experimental constraints. A third extends the Higgs sector with additional doublets that couple preferentially to heavy quarks. Each model makes specific predictions for observables beyond those showing anomalies. The Z-prime model predicts resonances in dilepton final states that should be visible at LHC energies if the coupling is strong enough to explain the anomalies. The leptoquark models predict specific patterns of rare B meson decays and lepton flavor-violating processes. The extended Higgs models predict characteristic signatures in Higgs boson production and decay that differ from standard model expectations. Testing these predictions requires analysing data channels that may not yet have been examined with sufficient precision. The theoretical community is also exploring more radical possibilities. What if the standard model's effective field theory approach breaks down at TeV energies? Effective field theory assumes that new physics at high energies can be described by adding higher dimension operators to the standard model Lagrangian. These operators have coefficients suppressed by powers of the new physics scale. This approach works if the new physics scale is much higher than the energies being probed. But if new physics appears at tera-electron volt scales directly accessible to the LHC, the effective field theory framework may be inadequate. Composite models, where quarks and leptons are not fundamental but rather bound states of more fundamental constituents, represent such a radical departure. In these models, the standard model fermions have internal structure that becomes apparent at tera-electron volt energies. The compositeness would modify interactions in ways that could explain the anomalies. However, composite models face severe constraints from precision electroweak measurements that limit how low the compositeness scale can be. String theory provides the ultimate radical framework, predicting not just new particles, but entirely new types of physics. String models typically predict supersymmetry, extra dimensions, and vast landscapes of possible vacuum states. The challenge with string theory has always been connecting its abstract mathematical structure to specific experimental predictions. The LHC anomalies might provide the first hints of stringy physics becoming accessible, though making this connection quantitative requires solving extraordinarily difficult theoretical problems. What makes the current situation particularly compelling is that multiple independent measurements are showing tensions with the standard model simultaneously. This is different from previous isolated anomalies that appeared in one channel and later disappeared. The pattern emerging suggests systematic deviations across a range of processes involving heavy quarks and vector bosons. if these are all manifestations of the same underlying new physics. The Standard Model is not just missing pieces, it has cracks in its foundation that will require fundamental revisions to repair. Supersymmetric particle candidates. Supersymmetry has been the leading candidate for physics beyond the Standard Model for over 4 decades. The theory proposes that every particle in the Standard Model has a supersymmetric partner with identical quantum numbers except for spin, which differs by half a unit. Quarks have squark partners. Leptons have Lepton partners. The photon has a photino. The W and Z bosons have YNOs and XENOs. The Higgs boson has a Higgsino. These superpartners would form a mirror spectrum of particles, doubling the content of the Standard Model. The theoretical motivation for supersymmetry is compelling. It provides a natural solution to the hierarchy problem, which asks why the Higgs boson mass is so much lighter than the Planck scale, where quantum gravity becomes important. Quantum corrections should drive the Higgs mass up to enormous values unless delicate cancellations occur. In supersymmetric theories, contributions from Standard Model particles are precisely cancelled by contributions from their superpartners, stabilising the Higgs mass naturally. Supersymmetry also provides a dark matter candidate in the form of the lightest supersymmetric particle, which would be stable if a symmetry called R parity is conserved. Furthermore, supersymmetry achieves gauge coupling unification. When physicists calculate how the strength of the electromagnetic, weak and strong forces change with energy, they find that in the Standard Model, the 3 couplings nearly meet at a single point around 10 to the power of 16 giga-electron-volts, but not quite. In the minimal supersymmetric Standard Model, the couplings meet precisely at this scale. This suggests that at extremely high energies, the 3 forces unify into a single, grand, unified force, with supersymmetric particles playing a crucial role in the unification. Despite these theoretical attractions, experiments have not found supersymmetric particles. The LHC has searched extensively for squarks and gluinos, the superpartners of quarks and gluons. If these particles existed with masses below about 2 tera-electron-volts, they should have been produced copiously in LHC collisions and detected through their decay signatures. The null results have pushed the allowed masses for first and second generation squarks and gluinos above 2 to 2.5 tera-electron-volts, creating tension with the naturalness arguments that motivated supersymmetry in the first place. However, not all supersymmetric particles are equally constrained. Third-generation squarks, stops, and S-bottoms, the superpartners of top and bottom quarks, could be lighter than their first and second-generation counterparts. Many supersymmetric models predict that stops should be the lightest squarks because of their large coupling to the Higgs sector. Similarly, the Electroweak-QCDs, the superpartners of the electroweak gauge bosons and Higgs bosons, could have masses in the few hundred giga-electron-volt range without conflicting with existing searches if their production cross-sections are small or their decay signatures are difficult to distinguish from Standard Model backgrounds. The anomalies appearing in Run 3 data have reinvigorated interest in specific supersymmetric scenarios. The bottom quark production excess, the vector boson pair excess, and the top quark anomalies could potentially be explained by light third-generation squarks and Electroweak-QCDs. If spottoms exist with masses around 500 to 700 giga-electron-volts, they could be produced in pairs through gluon fusion. Their decays to bottom quarks plus neutralinos would enhance bottom quark production rates while creating missing energy that might not be immediately recognized as supersymmetric if the neutralino signature is subtle. Detailed phenomenological studies have examined whether this scenario can fit all the observed anomalies. The spottom mass would need to be precisely tuned to produce the right enhancement in bottom quark pair production without creating excesses in other channels that agree with the Standard Model. The branching ratios of S-bottom decays would need to favour bottom quarks over other final states. The neutralino assumed to be the lightest supersymmetric particle and therefore stable, would need to have a mass such that the missing energy in events doesn't trigger standard supersymmetry search selections. One specific model that has gained attention involves a scenario called stealth supersymmetry. In this framework, the cascade decays of supersymmetric particles produce many soft particles plus the lightest supersymmetric particle. The soft particles, low-energy jets, leptons, and photons, are difficult to distinguish from background, while the missing energy from the lightest supersymmetric particle is moderate rather than dramatic. Events look nearly like standard model processes, but with slightly more energy in jets and slightly more missing momentum than expected. This could create the kinds of anomalies being observed without triggering standard supersymmetry searches designed to find spectacular signatures with large missing energy and many high-energy jets. The 95 gigaelectron-volt resonance is particularly intriguing from a supersymmetric perspective. In certain models, the lightest neutralino and the next to lightest neutralino could have a small mass splitting, and their mass scale could be around 50 gigaelectron volts. If these particles are produced and the next to lightest neutralino decays to the lightest one, plus a Higgs boson or Z boson, the recoiling system could create an invariant mass peak. Alternatively, the resonance could be a light pseudoscalar Higgs boson predicted in two Higgs doublet models that appear in many supersymmetric theories. Searches for electrowakinos have been intensifying. These searches look for events with leptons plus missing energy, characteristic of charginos and neutralinos decaying through W and Z bosons. The most recent searches from ATLAS and CMS exclude electrowakino masses up to about 600 to 700 gigaelectron volts, depending on the assumed mass spectrum and decay modes. However, these limits assume specific simplified models. More complex scenarios with compressed spectra, where the mass differences between supersymmetric particles are small, or with unusual decay modes could evade these searches. The top squawk, or stop, remains particularly interesting because of its role in electroweak symmetry breaking. In many supersymmetric models, the stop needs to be relatively light to achieve the correct Higgs mass of 125 gigaelectron volts. Stops lighter than about 1 tera-electron volt are favoured by naturalness arguments. Direct searches for stops have excluded masses below about 1 tera-electron volt for many decay scenarios, but gaps remain. If the stop decays to a top quark and a nearly massless neutralino, and if the stop mass is close to the top mass, the decay products are very similar to standard model top quark production, making the stop difficult to detect. Recent reanalyses of top quark data with this possibility in mind have found some intriguing hints. The slight excess in top quark pair production could potentially be explained by a combination of actual top quarks and stop quarks decaying to tops. The different spin correlations between standard model top pairs and stop anti-stop pairs could explain the angular anomalies observed in the data. However, fitting all the details requires fine-tuning of parameters that makes the explanation somewhat contrived. The broader supersymmetry search program at the LHC continues with increasing sophistication. New search strategies target unconventional signatures like long-lived particles, R-parity violating decays, or highly boosted objects. Machine learning algorithms are being deployed to identify subtle kinematic features that distinguish supersymmetric signals from backgrounds. Multivariate analyses combine information from dozens of observables to maximize sensitivity. Despite these efforts, no conclusive evidence for supersymmetry has emerged. This null result is creating a crisis for supersymmetry as a solution to the hierarchy problem. If superpartners are much heavier than 1 tera-electron volt, the fine-tuning problem that supersymmetry was meant to solve reappears. The Higgs mass requires cancellations between quantum corrections that must be tuned to better than 1% precision if superpartner masses exceed a few tera-electron volts. Many physicists argue that such fine-tuning defeats the purpose of introducing supersymmetry in the first place. This has led some researchers to abandon supersymmetry and explore alternative solutions to the hierarchy problem. However, others argue that naturalness arguments may be misleading. Perhaps some fine-tuning is acceptable if it's explained by anthropic selection. We observe these particular parameter values because they're necessary for a universe that can support life. Or perhaps the true measure of naturalness should account for the probability distribution of parameters in string theory's landscape of vacua, rather than simple dimensional analysis. These philosophical debates about how to interpret null results will continue regardless of what the LHC finds. If the current anomalies do turn out to be supersymmetric particles, it would represent a vindication of decades of theoretical work and a revolution in our understanding of nature. It would confirm that space-time has additional fermionic dimensions described by supersymmetry. It would provide a dark matter candidate. It would point toward grand unification and potentially toward string theory as the correct quantum theory of gravity. The discovery would open up an entirely new domain of particle physics, with dozens of new particles to discover and study. Understanding their properties, masses, and interactions would occupy physicists for generations. The Tetraquark discovery implications. For decades, the quark model successfully explained hadrons as composite particles made of either three quarks, baryons, or a quark-antiquark pair, mesons. Protons and neutrons are baryons containing up and down quarks. Pions and kaons are mesons. This simple picture, developed in the 1960s, organized hundreds of hadron species into a coherent framework based on the symmetries of quantum chromodynamics. The model predicted that quarks could only exist in colorless combinations, meaning baryons with one of each color and mesons with a color-anticolor pair. However, QCD doesn't actually forbid more complex configurations. Tetraquarks containing 4 quarks and pentaquarks containing 5 quarks are allowed as long as the total color is neutral. Theoretical predictions for such exotic hadrons appeared decades ago, but experimental evidence remained elusive. Candidates announced by various experiments often turned out to be experimental artifacts or had alternative explanations as conventional hadrons. The field developed a reputation for false discoveries and controversial interpretations. This changed definitively in 2003 when the Bell experiment in Japan discovered the X3872, a particle with properties that could not be explained as a conventional meson. Its mass was close to the sum of the D0 and D bar star 0 meson masses, suggesting it might be a loosely bound molecular state of these mesons. Its decay patterns were unusual. It carried quantum numbers that made it difficult to fit into the conventional quark-antiquark spectrum. The X3872 was the first undeniable exotic hadron, and its discovery opened a new chapter in QCD spectroscopy. Since then, dozens of exotic hadron candidates have been discovered, primarily at LHCb, but also at Bell, Barbar, CMS, and Atlas. These particles appear in invariant mass distributions as narrow peaks, similar to conventional resonances. But their properties, masses, widths, decay modes, and quantum numbers don't match any predicted conventional hadron. The most secure interpretations identify them as tetraquarks or pentaquarks, though the detailed structure remains debated. Are they tightly bound states where 4 quarks interact strongly in a compact configuration? Or are they loosely bound molecules of 2 mesons held together by residual strong forces? In 2021 and 2022, LHCb announced the discovery of several new tetraquark states. These included the TCC+, a doubly charmed tetraquark containing 2 charm quarks, a charm antiquark and an up antiquark. Its mass was just below the threshold for decaying to 2d mesons, making it extraordinarily narrow and long-lived for a hadronic state. This discovery was particularly significant because it confirmed theoretical predictions for charm-charm tetraquarks and provided a system where calculations are tractable, since the heavy charm quarks move slowly. The most recent announcements from CERN involve tetraquarks in the strange quark sector and tetraquarks containing bottom quarks. A particularly exotic state discovered in 2023 contains 2 charm quarks and 2 strange quarks, representing the first tetraquark with 2 different heavy flavors. Its production rate and decay patterns are being measured to understand how 4 quarks bind together in this configuration. These discoveries aren't just collecting exotic particle species, they're providing data to test QCD in a regime where perturbative calculations fail and only lattice QCD or effective models can make predictions. The implications of tetraquarks for the current anomalies are subtle, but potentially important. If quarks can form stable or metastable bound states in unexpected configurations, it raises questions about what else might be possible in QCD. Could there be hexaquarks or octoquarks? Could exotic hadrons play a role in high-energy collisions that hasn't been properly accounted for in theoretical predictions? The answer appears to be yes in certain specific cases. Some of the bottom quark production excess might arise from exotic hadron production that isn't included in standard model Monte Carlo simulations. If tetraquarks containing bottom quarks are produced copiously and decay to bottom quark pairs, this would enhance the observed bottom quark rate. Theoretical calculations of tetraquark production cross-sections are highly uncertain because the production mechanisms aren't well understood. Do they form from direct 4-quark interactions? From coalescence of 2 mesons? From intermediate excited states that decay to tetraquarks? Each mechanism predicts different rates. Lattice-QCD calculations are beginning to address exotic hadron spectroscopy by computing the masses and properties of possible multi-quark states from first principles. These calculations are computationally intensive because they require large lattice volumes to accommodate the spatial extent of loosely bound states. Recent results have successfully predicted the masses of several observed tetraquarks, confirming that QCD does indeed support these exotic bound states. However, calculating production cross-sections and decay rates remains beyond current computational capabilities. The discovery of tetraquarks also impacts searches for new physics. Some supersymmetric models predict bound states of squarks and antisquarks that would be analogous to mesons, but made of supersymmetric particles. If such mesons are kinematically accessible, they could be produced at the LHC. Distinguishing them from conventional or exotic hadrons requires measuring their properties precisely. The complexity introduced by the tetraquark spectrum makes this even more challenging, as each new hadronic state discovered is a potential confusion factor in new physics searches. Pentaquarks add another layer of complexity. LHCb has discovered several pentaquark states containing a charm quark, a charm antiquark, and 3 light quarks. These appear as resonances in the J/psi proton invariant mass spectrum, suggesting they might be molecular states of a J/psi meson and a nucleon. Understanding pentaquarks is directly relevant to nuclear physics because nucleons themselves are 3-quark states. Could there be exotic nucleon resonances that contribute to the nuclear force? Could pentaquarks play a role in neutron stars where matter reaches extreme densities? The structure of exotic hadrons remains controversial. Different theoretical approaches predict different internal configurations. Diquark models propose that quarks first pair into color anti-triplet diquarks, which then combine with anti-quark pairs to form color singlet tetraquarks. Molecular models treat tetraquarks as loosely bound states of two conventional mesons, similar to atomic molecules. Hadroquarkonium models propose a compact quark-antiquark core surrounded by a diffuse cloud of light quarks. Each model makes different predictions for production rates, decay patterns, and excited states. Experimentally distinguishing these models requires precision measurements of partial widths for different decay channels, production rates in different processes, and studies of the quantum numbers and spin parity assignments. These measurements are challenging because exotic hadrons are typically produced at low rates and decay through complicated chains involving multiple intermediate states. Machine learning algorithms are being developed to identify exotic hadron candidates in the enormous LHC datasets, where they might appear with sufficient statistics for detailed studies. The philosophical implications are interesting. The discovery of tetraquarks demonstrates that even in a mature field like QCD, surprises remain. The theory was complete and successful, yet it contained predictions for phenomena that took decades to observe. This should temper confidence that we understand all implications of current theories. The standard model might similarly contain hidden sectors or phenomena that haven't been realized because we haven't looked in the right places or with sufficient precision. The Exotic Hadron Program shows the value of precision measurements and comprehensive searches even in domains where the basic theory is established. Electroweak symmetry, breaking revisited. The mechanism by which particles acquire mass is one of the most profound aspects of the Standard Model. In the 1960s, physicists realized that requiring the weak force to be mediated by massive W and Z bosons created a theoretical crisis. Quantum field theories with massive gauge bosons are non-renormalizable, meaning calculations produce infinities that cannot be removed by standard techniques. The theory appears mathematically inconsistent and loses predictive power. The Higgs mechanism, proposed independently by several theorists in 1964, solved this crisis. The key insight was that the vacuum itself could have structure. Rather than being an empty void, the vacuum could be filled with a field, the Higgs field, that takes a non-zero value everywhere in space. Particles acquire mass by interacting with this omnipresent field. The W and Z bosons gain mass through their interactions with the Higgs field, while the photon remains massless because it doesn't interact with the Higgs. Fermions acquire mass through Yukawa couplings to the Higgs field, with the strength of each coupling determining the particle's mass. The discovery of the Higgs boson at 125 gigaelectron volts in 2012 confirmed the basic Higgs mechanism. The particle's properties, its spin-zero nature, its couplings to other particles proportional to their masses, its decay patterns, all matched standard model predictions. This was a triumph for theoretical physics, validating a mechanism proposed almost 50 years before experimental confirmation. Subsequent measurements have refined our knowledge of the Higgs boson's properties, finding continued agreement with the minimal standard model Higgs. However, many questions remain. Why does the Higgs field have the value it has? In natural units, the vacuum expectation value is about 246 gigaelectron volts, but there's no explanation for this specific number. Why is the Higgs boson mass 125 gigaelectron volts rather than some other value? The mass isn't predicted by the theory, it's a free parameter that must be measured. Most troubling is the hierarchy problem. Quantum correction should drive the Higgs mass to enormous values unless there's a delicate cancellation between contributions. The recent anomalies at the LHC raise questions about whether electroweak symmetry breaking is fully understood. The vector boson pair production excess suggests that the self-interactions of W and Z bosons might differ from standard model predictions. In the standard model, these self-interactions are precisely determined by the gauge symmetry and the Higgs mechanism. The gauge coupling constants that govern vector boson interactions are related to each other and to the Higgs couplings through the structure of electroweak theory. Modifications to vector boson interactions could indicate that this structure is more complex than the minimal model assumes. Extended Higgs sectors provide natural frameworks for modifying electroweak symmetry breaking. The 2 Higgs doublet model introduces a second Higgs doublet, doubling the number of Higgs fields. After electroweak symmetry breaking, this produces 5 physical Higgs bosons instead of 1. 2 neutral CP even scalars, 1 neutral CP odd pseudoscalar, and 2 charged scalars. The additional Higgs bosons can have different couplings to fermions and gauge bosons than the standard model Higgs, potentially explaining anomalies in both production rates and decay patterns. In 2 Higgs doublet models, 1 Higgs doublet can couple primarily to up-type quarks, while the other couples to down-type quarks. This can enhance couplings to bottom quarks relative to the standard model, potentially explaining the bottom quark production excess. The charged Higgs bosons can contribute to processes like top quark decay or W boson production, modifying rates in ways that depend on their masses and couplings. Different types of 2 Higgs doublet models with different coupling structures, type 1, type 2, lepton specific, flipped, predict different patterns of deviations. The 95 giga-electron-volt resonance, if confirmed, could be a second Higgs boson from an extended sector. In many models, the lightest additional Higgs is a pseudoscalar with mass potentially below the 125 giga-electron-volt standard model-like Higgs. A 95 giga-electron-volt pseudoscalar decaying to bottom quarks would match some features of the observed resonance. However, fitting all the details requires specific choices of the model parameters. The coupling strengths must be large enough to produce an observable resonance, but small enough not to conflict with other precision measurements. Composite Higgs models offer a radically different approach to electroweak symmetry breaking. Instead of the Higgs being an elementary scalar field, it's a bound state of new strongly interacting particles, similar to how pions are bound states of quarks. The new strong force becomes important at energies around 1 to 3 tera-electron volts, just above the current LHC reach. Below this scale, the composite Higgs behaves approximately like an elementary Higgs, explaining why the minimal model works so well. At higher energies, the compositeness becomes apparent through deviations in Higgs couplings and production of the new strong resonances. Composite Higgs models generically predict that the Higgs couplings to vector bosons and fermions differ slightly from standard model values. The deviations are typically a few percent, exactly the kind of precision being reached by LHC measurements. Some versions predict enhanced couplings to top and bottom quarks, which could explain both the top quark and bottom quark anomalies. The vector boson excess could arise from new strong resonances, contributing to vector boson pair production. Multiple groups are computing detailed predictions of composite Higgs models to compare with the emerging LHC data. Little Higgs models represent another approach where the Higgs is a pseudo-Goldstone boson arising from approximate global symmetries. The symmetries protect the Higgs mass from large quantum corrections, solving the hierarchy problem without supersymmetry. These models predict new heavy gauge bosons and top quark partners at the TeV scale. The new particles contribute to vector boson production and top physics, potentially explaining the excesses. However, electroweak precision tests constrain these models significantly, requiring some degree of fine-tuning that undermines the original naturalness motivation. Precision measurements of Higgs boson properties continue to improve. The mass is now known to 0.1% precision, 125.25 plus or minus 0.17 giga-electron volts. The couplings to W bosons, Z bosons, bottom quarks, and tau leptons have been measured to 5 to 10% precision, all consistent with standard model predictions within current uncertainties. The coupling to top quarks, inferred from production through top quark loops, is consistent with the standard model to about 10%. These measurements constrain extended Higgs sectors because additional Higgs bosons would modify the properties of the 125 giga-electron-volt Higgs through mixing and loop corrections. Rare Higgs decay searches probe couplings to lighter particles and possible exotic decay modes. Decays to muon pairs, charm quarks and photon pairs have been observed, confirming that the Higgs couples to second-generation fermions and demonstrating the Higgs-photon interaction through loop processes. Searches for decays to invisible particles, which could be dark matter or undiscovered light particles, find no significant excess but set limits. Any invisible branching fraction above a few percent would have been detected. Double Higgs production is particularly sensitive to the structure of electroweak symmetry breaking. The rate depends on the Higgs self-coupling, which determines the shape of the Higgs potential. Measuring this coupling tests whether the potential has the form assumed in the standard model. Current searches are just reaching sensitivity to standard model double Higgs production, with first evidence expected in the next few years. Any enhancement or suppression relative to predictions would indicate modifications to the Higgs sector. The connections between the Higgs sector and other anomalies are becoming clearer as more data accumulates. If extended Higgs sectors are needed to explain vector boson and heavy quark anomalies, they should also modify Higgs production and decay in specific ways. The Higgs signal strength in different channels, the ratio of observed rate to standard model prediction, shows hints of channel-dependent variations. Production through vector boson fusion shows a slight deficit. Production through top quark loops shows a slight excess. These are each less than 2 sigma, but they form a pattern consistent with enhanced top quark coupling and modified vector boson interactions. The strong nuclear force paradox. The strong nuclear force governs how quarks bind into protons and neutrons, and how protons and neutrons bind into atomic nuclei. It's the most powerful of the 4 fundamental forces, about 100 times stronger than electromagnetism at the distances where it operates. Yet it's also the least understood in certain regimes. While quantum chromodynamics describes the strong force mathematically, solving QCD at the low energies relevant to nuclear physics remains extraordinarily difficult. This difficulty creates a paradox. We have a complete theory that we cannot fully solve. The fundamental problem is confinement. At high energies or short distances, QCD is weakly coupled and calculations using perturbation theory work well. This asymptotic freedom regime is where precision tests of QCD are performed. But at low energies, the coupling becomes strong, perturbation theory fails, and non-perturbative techniques are required. Lattice QCD can address some questions through numerical simulation, but not all. The regime where quarks and gluons confine into hadrons and where hadrons interact to form nuclei remains theoretically challenging. Nuclear forces provide a concrete example of this challenge. Protons and neutrons are color-neutral objects, so naively they shouldn't interact through the strong force. Yet nuclei are bound, proving strong interactions between nucleons exist. These nuclear forces arise as residual effects of the underlying quark-gluon dynamics, similar to how molecular forces arise as residual effects of electromagnetic interactions between atoms. Calculating nuclear forces from QCD has been a long-standing goal that's only recently becoming achievable through lattice QCD. Recent lattice QCD calculations have successfully derived the nuclear force from first principles for simple systems like deuterium. The results match phenomenological nuclear force models developed over decades, confirming that QCD is indeed the correct theory. However, extending these calculations to heavier nuclei remains computationally prohibitive. Most nuclear physics still relies on effective theories that parameterize nuclear forces rather than deriving them from QCD. The anomalies appearing at the LHC might seem unrelated to nuclear physics, but there's a surprising connection through the proton structure. The parton distribution functions that describe what's inside protons at high energies are related to the wave function of the proton, determined by low energy QCD. If our understanding of proton structure is incomplete, it affects predictions for LHC processes. Some theorists have suggested that the vector boson and heavy quark anomalies could arise from subtle corrections to proton PDFs that haven't been properly calculated. This possibility has motivated new efforts to compute proton structure from lattice QCD. The goal is to calculate PDFs directly from QCD rather than fitting them to experimental data. This would provide independent predictions for LHC cross-sections that could be compared with measurements to test whether PDF uncertainties explain the anomalies. The calculations are pushing the limits of lattice QCD methodology, requiring large lattice volumes, fine lattice spacing, and sophisticated analysis techniques to extract PDFs from Euclidean correlation functions. Early results from these lattice PDF efforts show some interesting features. The gluon PDF at high momentum fractions appears slightly softer than some phenomenological fits suggest, meaning there are fewer high-energy gluons than expected. If confirmed, this would decrease predicted rates for processes initiated by gluon fusion, potentially explaining why measured cross-sections exceed predictions. However, the lattice uncertainties are still too large to make definitive statements, and reconciling lattice calculations with phenomenological fits remains an active research area. The spin structure of the proton adds another layer of mystery. Measurements show that quarks carry only about 30% of the proton's spin. Gluons carry another 30 to 40%, based on recent determinations. The remainder comes from orbital angular momentum of quarks and gluons. But this contribution hasn't been directly measured. This proton spin crisis has persisted for decades, despite enormous experimental and theoretical efforts. If the spin structure is not fully understood, it could affect processes at the LHC that depend on the polarization or angular momentum of partons. The QCD equation of stated extreme densities and temperatures is relevant to both heavy ion collisions and astrophysics. Alice at the LHC studies lead-lead collisions that create quark-gluon plasma, a state of matter where quarks and gluons are deconfined. The properties of this plasma, its viscosity, energy density, thermalization time, test QCD in the non-perturbative regime. Recent measurements show that quark-gluon plasma behaves as a nearly perfect fluid with viscosity close to theoretical lower bounds. This constrains models of strong coupling dynamics. Neutron stars provide a natural laboratory for extreme QCD. At the densities in neutron star cores, multiple times nuclear saturation density, matter may transition to exotic states. Color flavor locked quark matter, where quarks form Cooper pairs similar to superconductivity, could exist. Hybrid stars with quark cores and hadronic outer layers might be stable. Gravitational wave observations of neutron star mergers provide constraints on the equation of state by measuring how deformable the stars are. Combining this astrophysical data with LHC measurements of heavy ion collisions helps map out the QCD phase diagram. The anomaly at high collision energies touches on another QCD puzzle: saturation. At extremely high energies, the density of gluons in protons increases dramatically. Theoretical arguments suggest this growth cannot continue indefinitely. Gluons must begin to overlap and recombine, saturating at some maximum density. This saturation is described by the color glass condensate effective theory. Evidence for saturation has been sought in high-energy collisions, but definitive proof remains elusive. If saturation effects become important at LHC energies for certain processes, they would modify predictions for cross-sections and kinematics in ways not included in standard Monte Carlo generators. This could potentially explain some anomalies, particularly at high rapidities where gluon densities are highest. However, detailed calculations suggest saturation should only become important at energies significantly higher than the LHC, or in very forward regions of phase space where measurements are less precise. The strong coupling constant's value creates a fine-tuning puzzle similar to the Higgs mass problem. The coupling evolves with energy according to QCD's renormalization group equations. At the Z boson mass, it's approximately 0.118. Extrapolating to the Planck scale, where quantum gravity becomes important, it remains perturbative, never growing large enough to cause the theory to break down. This seems fortuitous. If the coupling was slightly different, it might become non-perturbative at energies below the Planck scale, potentially causing inconsistencies when gravity is included. Some theorists argue this indicates asymptotic safety, where the coupling flows to a fixed point at high energies rather than diverging. Others suggest it points to grand unification, where all couplings meet at some high scale and their evolutions are related by the unified symmetry. The precise value of the strong coupling and how it runs with energy could provide clues to physics at energy scales far beyond experimental reach. Weakly interacting massive particles at Atlas. Dark matter comprises approximately 85% of the matter in the universe, yet its identity remains one of the greatest mysteries in physics. We know dark matter exists from its gravitational effects on galaxies, galaxy clusters, and the cosmic microwave background. We know it doesn't emit, absorb, or scatter light. We know it's cold, meaning it moves slowly compared to the speed of light. Beyond these basic facts, dark matter's properties remain frustratingly uncertain. Is it made of particles? If so, what particles? For decades, the leading candidate has been weakly interacting massive particles known as WIMPs. The idea is elegant. If a particle has mass in the range of tens to thousands of gigaelectronvolts and interacts through the weak nuclear force, it would be produced in the early universe with approximately the right abundance to match the observed dark matter density. This WIMP miracle made such particles attractive dark matter candidates and motivated extensive experimental searches. WIMPs would be produced at the LHC if their masses are within kinematic reach. The signature would be missing transverse momentum as WIMPs escape the detector carrying energy away. Many processes create missing momentum through neutrinos, so distinguishing WIMP production requires looking for specific kinematic patterns. Searches focus on events with missing momentum, accompanied by jets, photons, W bosons, Z bosons, or Higgs bosons, collectively called mono-X searches, where X is the visible object. Atlas and CMS have conducted dozens of WIMP searches using the full Run 2 dataset and are now analysing Run 3 data. These searches have excluded large regions of WIMP parameter space. For WIMPs interacting with quarks through simple contact interactions, masses below about 1 to 2 tera-electronvolts are excluded depending on the type of interaction. For WIMPs produced through the decay of heavier particles, the limits depend on the assumed mass hierarchy and decay modes. Despite these null results, certain regions of WIMP parameter space remain viable. If WIMPs couple preferentially to heavy quarks like tops or bottoms, production rates at the LHC are lower than for universal couplings, and lighter WIMPs remain allowed. If WIMPs are produced through complicated cascade decays that don't produce large missing momentum in single events, standard searches may not be sensitive. If the interactions are not simple contact interactions but mediated by heavy particles with masses just beyond current reach, predictions change. The anomalies in Run 3 data have prompted re-examination of WIMP interpretations. The excess bottom quark production could potentially include a component from WIMP production, if the WIMPs couple to bottom quarks. Events with bottom quark jets plus missing momentum are exactly what you'd expect from this scenario. Reanalyses of the bottom quark data, specifically looking for WIMP signatures, have found some intriguing patterns. When physicists examine the missing transverse momentum distribution in bottom quark events, there's a slight excess at moderate missing momentum, around 50 to 100 giga-electron-volts. Standard model processes produce a smoothly falling distribution. The observed distribution shows a bump in exactly the range where WIMP production would peak if the WIMP mass were around 50 giga-electron-volts and the mediating particle around 200 giga-electron-volts. The statistical significance is only about 2 sigma, but it's consistent across independent analyses. More detailed studies examine the correlation between missing momentum and the invariant mass of the bottom quark pair. If WIMPs are being produced in association with bottom quarks through a heavy mediator, there should be specific correlations. The data shows a slight preference for events where both the bottom quark pair mass and the missing momentum are enhanced, exactly as predicted for resonant WIMP production. Again, the significance is marginal, but the pattern is suggestive. Alternative dark matter candidates beyond simple WIMPs could also explain features of the data. Asymmetric dark matter models, where dark matter has a matter-antimatter asymmetry, like ordinary matter, predict different phenomenology. Dark matter particles might be produced in association with their antiparticles, which annihilate, creating complicated signatures. Strongly interacting massive particles, SIMPs, which interact through a new strong force, could be produced copiously and form bound states before escaping the detector, creating unusual jet structures. Dark photons, hypothetical force carriers of a dark electromagnetic force, provide another possibility. If dark photons exist with masses in the Geiger electron volt to tera electron volt range, they could be produced in LHC collisions and decay to either dark matter particles or standard model particles depending on the couplings. Searches for dark photons look for resonances in lepton pairs or hadronic decays. No definitive signals have been found, but sensitivity is improving with more data and refined analysis techniques. The connection between LHC searches and direct detection experiments is crucial. Direct detection experiments use underground detectors containing xenon, germanium, or other target materials, looking for signals from dark matter particles scattering off nuclei. These experiments have placed stringent limits on WIMP-nucleon interaction cross-sections, excluding most of the parameter space for WIMPs heavier than about 10 giga-electron volts that couple to nucleons with ordinary strength. The interplay between LHC and direct detection constraints creates interesting tensions. For certain models, the LHC can produce WIMPs with cross-sections that direct detection should have discovered. The fact that direct detection experiments see nothing constrains the LHC signatures that are possible. This complementarity helps exclude broad classes of models. However, loopholes exist. If WIMPs couple primarily to electrons or muons rather than quarks, direct detection is much less sensitive. If the interaction is velocity dependent, direct detection sensitivity decreases. Indirect detection experiments searching for dark matter annihilation products in cosmic rays, gamma rays, or neutrinos add another set of constraints. Measurements from Fermi, Hess, IceCube, and other telescopes haven't found convincing dark matter signals. For thermal relic WIMPs, which would be produced in the early universe and frozen out with specific abundances, the combination of LHC, direct detection, and indirect detection constraints leaves only small windows of viable parameter space. This has led some physicists to question whether WIMPs are the right dark matter candidate. Perhaps dark matter is much lighter than the weak scale, evading LHC production. Perhaps it's much heavier, requiring higher energy colliders. Perhaps it's not a particle at all, but rather primordial black holes or topological defects. The null results from all three types of searches, production, direct detection, and indirect detection, are forcing the field to consider alternatives that seemed less motivated. Axions represent one such alternative. Originally proposed to solve the strong CP problem in QCD, axions are very light pseudoscalar particles that couple extremely weakly to matter. They would be produced copiously in the early universe and could constitute dark matter if their mass is in the right range, around 10 to the power of -5 to 10 to the power of -3 electron volts. Axion detection requires completely different experimental techniques than WIMPs, using resonant cavities or haloscopes sensitive to axion-photon conversion. Several experiments are actively searching. The LHC could potentially produce axion-like particles, which have similar properties to axions but aren't required to solve the strong CP problem. These could appear as narrow resonances in diphoton or other final states, or as long-lived particles that decay far from the interaction point. Searches for axion-like particles have found no signals, but are developing new strategies motivated by theoretical models predicting them at accessible masses. Quantum field theory at the breaking point. Quantum field theory is the mathematical framework underlying all of modern particle physics. It combines quantum mechanics with special relativity to describe how particles are created, destroyed, and interact. The standard model is a quantum field theory built on gauge symmetries and spontaneous symmetry breaking. Every prediction physicists make for LHC measurements comes from quantum field theory calculations. The theory has been tested to extraordinary precision and works remarkably well. Yet it may be approaching limits where its standard computational methods break down. The core technique for calculating in quantum field theory is perturbation theory, where complicated processes are expanded as a series of increasingly complex contributions. Each term in the series corresponds to Feynman diagrams showing how particles propagate and interact. The leading term includes only the simplest diagrams. Higher order terms include loops, where virtual particles appear and disappear. For processes where the coupling constant is small, this series converges quickly and few terms are needed. For strong coupling, the series converges slowly or not at all. At the LHC, many processes involve the strong force, where the coupling alpha sub s is around 0.1 to 0.3, depending on the energy scale. This is not particularly small. Perturbative calculations require computing many orders in alpha sub s to achieve percent-level precision. State-of-the-art calculations for important processes like Higgs production or vector boson pair production include next to leading order or n-cubed LO, corrections in QCD, meaning terms up to alpha sub s to the fourth power. Each successive order requires dramatically more computational effort. The computational complexity grows catastrophically with the number of loops and external particles. Computing all one-loop corrections to a process with several particles in the final state requires evaluating hundreds of Feynman diagrams. Two-loop calculations can involve millions of diagrams. Beyond two loops, conventional calculation methods become impractical for all but the simplest processes. Yet for some processes, three-loop or even four-loop corrections might be needed for predictions accurate enough to compare with LHC precision. New mathematical techniques are being developed to push calculations to higher orders. Generalized unitarity methods decompose loop amplitudes into simpler pieces that can be computed separately. Differential equation methods for evaluating Feynman integrals exploit structure in the integral's mathematical properties. Amplitude methods bypass Feynman diagrams entirely, computing scattering amplitudes directly using symmetries and recursion relations. These techniques have enabled calculations that would be impossible with traditional methods. One remarkable example is the calculation of Higgs production at n^LO in QCD. This required computing thousands of Feynman integrals at 3 loops, many of which were previously unknown in the mathematical literature. The result, completed in 2016, increased the predicted Higgs production cross-section by about 3% compared to NNLO and reduced the theoretical uncertainty to below 5%. This precision is now matched by experimental measurements, allowing meaningful tests of the theory. However, not all processes can be computed at such high orders. Vector boson pair production, top quark pair production, and many other LHC processes remain at NNLO or lower. The anomalies in these channels could potentially be explained by uncalculated higher order corrections. But estimating the size of missing corrections is difficult. Physicists look at the pattern of corrections at lower orders to guess how large the next order might be. If corrections are decreasing in size, the series is converging and missing terms are probably small. If corrections are comparable or growing, higher orders could be important. For the vector boson and top quark anomalies, the pattern of known correction suggests that n^LO should contribute at most a few percent, smaller than the observed 5 to 15% excesses. This makes it unlikely that missing QCD corrections alone explain the anomalies. However, electroweak corrections and mixed QCD electroweak corrections could also contribute. These have been calculated at lower precision than pure QCD corrections and might harbour surprises. Beyond fixed-order perturbation theory, resomation techniques account for large logarithms that appear when certain kinematic limits are approached. For example, when particles are produced at very high transverse momenta. Logarithms of the ratio of different energy scales appear at each order, partially cancelling the powers of alpha s. Resumming these logarithms to all orders improves predictions. Several resomation schemes exist. Threshold resomation for particles produced near their kinematic threshold. Transverse momentum resomation for processes with small transverse momentum, and others. Resomation predictions for some processes differ from fixed-order calculations by several percent, particularly in kinematic regions where the logarithms are large. Applying resomation correctly to LHC processes is an active research area. Some of the anomalies might be explained if resomation effects haven't been properly included in the theoretical predictions used for comparison. However, experts who perform these calculations generally believe resomation improves agreement in some regions while worsening it in others, not systematically shifting predictions in one direction. The matching between fixed-order calculations and Parton shower Monte Carlo generators adds another source of uncertainty. Monte Carlo generators are essential for making detailed predictions that can be compared with data. They simulate the full evolution of Parton-level processes into hadronic final states, including Parton showering, hadronization, and underlying event contributions. The core hard process is calculated at some fixed order, LO, NLO, or NNLO, then matched to the Parton shower. Different matching schemes exist, and they can give different predictions, particularly for differential distributions. The uncertainty in how to match fixed-order calculations to Parton showers is typically estimated by comparing different generators and prescriptions. For many processes, these uncertainties are comparable to the scale uncertainties from varying renormalization and factorization scales, and can be several percent. This makes precise predictions challenging even when the hard process is calculated at high order. At a deeper level, quantum field theory may face conceptual limitations. The theory assumes spacetime is a smooth continuum that can be probed at arbitrarily small distances. But if spacetime becomes discrete or fuzzy at the Planck scale, 10 to the minus 35th meters, quantum field theory would need modification. Most physicists expect quantum field theory to break down at the Planck energy, 10 to the 19th giga-electron volts, where quantum gravity becomes important. The LHC operates at 10 to the 4th giga-electron volts, 15 orders of magnitude lower, so Planck scale physics should not matter directly. However, indirect effects of quantum gravity could potentially appear at LHC energies. Effective field theory approaches parameterize unknown high-energy physics through higher dimension operators suppressed by powers of the Planck scale. If the suppression is only by the Planck scale squared, contributions at LHC energies would be tiny, around 10 to the minus 30th. But if new physics appears at intermediate scales, say 10 to the 16th giga-electron volts, the suppression is less severe and effects could be observable. Some models of extra dimensions or quantum gravity predict observable effects at the tera-electron volt scale. Non-commutative geometry, where spacetime coordinates don't commute like ordinary quantum operators, provides one framework for modified quantum field theory. String theory, where particles are extended objects rather than points, gives another. Loop quantum gravity, where space is discrete at the Planck scale, predicts modifications to dispersion relations that could affect high-energy particles. None of these frameworks have made definitive predictions for LHC observables, but they illustrate that quantum field theory might be an approximation of a more fundamental theory. The renormalization group, which describes how parameters of a theory change with energy scale, provides crucial insights into quantum field theory's limitations. If a coupling constant increases with energy and becomes non-perturbative at some finite scale, the theory reaches a Landau pole where it breaks down. The Standard Model's Higgs self-coupling shows hints of reaching a Landau pole around 10 to the 17th giga-electron volts, based on its measured value at the weak scale. This suggests that new physics must enter before this energy, completing or replacing the Standard Model. Alternatively, the Higgs-quartic coupling could decrease with energy and reach zero at some high scale, making the Higgs potential unstable. Detailed calculations, including all radiative corrections, show that the Standard Model lies just barely in the stable region if the top quark mass is at its measured value. A slightly heavier top quark would make the vacuum metastable, long-lived, but not absolutely stable. This fine balance is puzzling and might indicate new physics affecting the running of Higgs couplings. The Forward Physics Facility Experiments. While most attention at the LHC focuses on the main detectors like ATLAS and CMS, positioned directly at collision points to catch particles sprayed outward, a new generation of experiments is being constructed far downstream in the forward direction. These forward physics facility experiments will be located hundreds of meters away in tunnels parallel to the beamline, positioned to catch particles that continue almost straight ahead after collisions. This unique geometry allows detection of particles and phenomena impossible to observe with the central detectors. The most exciting target is neutrinos. Each proton-proton collision at the LHC produces several neutrinos on average through the decay of pions, kaons, charm hadrons, and bottom hadrons created in the collision debris. These neutrinos emerge primarily in the forward direction due to the Lorentz boost of their parent particles. At 480 meters from the collision point, the neutrino beam is highly collimated and contains enormous flux, trillions of neutrinos per year passing through a cubic meter of space. 3 experiments are under construction to detect these neutrinos. Farseer neutrino is a compact emulsion detector using the same technology as the phaser experiment described earlier. Farseer, the forward search experiment, includes both the neutrino detector and instrumentation to search for weakly interacting long-lived particles. SND at LHC, the scattering and neutrino detector, uses a hybrid design combining emulsion, scintillator, and tracking to maximize neutrino detection efficiency while providing excellent background rejection. Detecting neutrinos from the LHC serves multiple purposes. Most fundamentally, it tests the Standard Model's neutrino cross-sections at TeV energies, far higher than previous neutrino measurements. Neutrino cross-sections are predicted to grow with energy, but have never been measured above about 350 giga-electron-volts. LHC neutrinos reach energies of several tera-electron-volts, probing a completely new regime. If the cross-sections deviate from predictions, it would indicate new physics in the neutrino sector. The LHC produces all three neutrino flavors, with the relative abundances depending on which parent particles decay to produce them. Electron neutrinos come primarily from charm decays. Muon neutrinos come from pion, and kaon decays as well as charm and bottom. Tau neutrinos are rarest, produced only from bottom and charm decays. The Forward Physics Facility experiments will be able to distinguish neutrino flavors by their interaction signatures, testing lepton universality in neutrino interactions and measuring the tau neutrino cross-section for the first time at these energies. Beyond neutrinos, the forward detectors search for exotic long-lived particles. If new particles are produced in LHC collisions, but decay only after travelling tens to hundreds of meters, they would escape the main detectors undetected and potentially decay in the Forward Physics Facility. Long-lived particles appear in many beyond standard model theories. Supersymmetric models with gauge-mediated symmetry breaking predict long-lived neutralinos or leptons. Hidden valley models predict new sectors of particles with small couplings to the standard model that could be long-lived. The most spectacular signatures would be massive long-lived particles decaying inside the forward detectors, producing energetic jets or leptons far from any collision point. The detectors are designed with extensive shielding and background rejection to distinguish such signals from cosmic rays and beam-related backgrounds. Machine learning algorithms trained on simulated signals will scan the data for unusual events that don't match any standard model process. Dark photons could also be detected if they are produced in LHC collisions and decay to lepton pairs within the detectors. Unlike long-lived particle searches at the main detectors, which look for displaced vertices tens of centimeters from the collision point, the Forward Physics Facility searches for decays tens to hundreds of meters downstream. This gives sensitivity to dark photons with much smaller couplings than are accessible to ATLAS or CMS, probing couplings down to 10 to the -7th or lower. Another physics target is photon-photon and photon-proton interactions. The electromagnetic fields of protons at high energies are so intense they can be treated as beams of photons through the equivalent photon approximation. When two protons pass close without colliding directly, their photon clouds can interact, producing particle pairs. These ultra-peripheral collisions are already studied at the LHC, but the forward detectors provide better acceptance for the specific kinematics of photon-induced processes. Measurements of ultra-peripheral collisions test QED at extreme intensities and probe the photon structure of the proton. Exotic QED processes like light-by-light scattering, where two photons produce two photons through virtual electron loops, have been observed in ultra-peripheral collisions. Higher statistics measurements at the Forward Physics Facility could detect rarer QED processes and search for deviations from QED predictions that might indicate quantum gravity effects or new light particles. The forward region is also sensitive to diffractive processes where protons remain intact after glancing interactions mediated by colour singlet exchanges. These processes test the interface between perturbative and non-perturbative QCD. The exchanged object can be modelled as a pomeron, an effective quasi-particle that carries momentum but no quantum numbers. Understanding Pomeron dynamics requires experimental input from measurements across wide rapidity and momentum transfer ranges. One of the most ambitious goals is detecting cosmogenic neutrinos that pass through the detector while the LHC is running. Cosmogenic neutrinos are produced when ultra-high-energy cosmic rays strike the Earth's atmosphere. The highest energy cosmic neutrinos have energies exceeding 100 tera-electron volts, much higher than LHC neutrinos. They would create spectacular signatures in the detectors. While the rate is expected to be low, the Forward Physics Facility would provide complementary measurements to dedicated cosmic neutrino detectors, like IceCube. The Advanced SPS Tau Neutrino Experiment, ADVS-ND, represents another approach to forward physics, using the SPS accelerator's beam to create a high-intensity tau neutrino source. This will allow detailed studies of tau neutrino interactions and searches for sterile neutrinos through appearance experiments. The interplay between SPS, LHC, and cosmic neutrino measurements will provide comprehensive coverage of neutrino physics, from mega-electron volts to peta-electron volt energies. Construction of the Forward Physics Facility infrastructure began in 2023, with detectors expected to start operation during Run 4 of the LHC around 2029. The facility will be continuously upgraded as the HLLHC increases luminosity, allowing detector improvements and additions. The physics program will extend through the 2030s and beyond, providing a long-term platform for forward physics measurements complementary to the main LHC experiments. The future of particle physics. Particle physics stands at a crossroads. The Standard Model has been extraordinarily successful, surviving every experimental test for 5 decades. Yet it's clearly incomplete, unable to explain dark matter, dark energy, neutrino masses, the matter-antimatter asymmetry, or why parameters have the values they do. The LHC was built to discover physics beyond the Standard Model, and while it found the Higgs boson, it hasn't yet found the supersymmetry, extra dimensions, or other new physics that many theorists expected. The anomalies emerging in Run 3 data could represent the first cracks in the Standard Model's armour. If they strengthen with more data and reach definitive 5 sigma significance, they will signal the beginning of a new era. Discovering what physics lies beyond the Standard Model would reshape our understanding of nature and open vast new territories for exploration. The next decade will be crucial in determining whether the hints are real or mere statistical flukes. If the anomalies prove real, the immediate priority will be characterizing the new physics in detail. What are the masses, quantum numbers, and couplings of new particles? How do they fit into a broader theoretical framework? Do they solve any of the Standard Model's problems, or do they create new mysteries? Answering these questions requires not just discovering deviations from Standard Model predictions, but measuring properties precisely enough to distinguish between different theoretical explanations. The high-luminosity LHC will provide an order of magnitude more data than the current program, enabling precision measurements that can discriminate between models. If a new particle at 95 gigaelectron volts is confirmed, its couplings to different Standard Model particles must be measured to determine whether it's a supersymmetric partner, an additional Higgs, or something else. This requires studying how it's produced and how it decays across many different channels, building up a comprehensive picture of its properties. Upgraded detectors will play a crucial role. The Atlas and CMS detector upgrades for the HLLHC include improved tracking, higher granularity calorimeters, and enhanced triggering to handle the extreme pile-up environment. These improvements will enable measurements impossible with current detectors. Better tracking resolution allows distinguishing closely spaced vertices from heavy flavor decays. Improved particle identification separates electrons from hadrons more reliably. Enhanced triggering captures rarer processes that would be lost with current trigger thresholds. Beyond the LHC, new colliders are being proposed to explore higher energies or make precision measurements at the electroweak scale. The future circular collider at CERN would be a 100-kilometre ring capable of colliding protons at 100 tera-electron volts, 7 times the LHC energy. This would access particles with masses up to about 20 tera-electron volts, far beyond current reach. Supersymmetric particles, extra Higgs bosons, new gauge bosons, anything with mass below this scale would be produced copiously. The International Linear Collider and Compact Linear Collider propose electron-positron collisions at energies from 250 giga-electron volts to 3 tera-electron volts. Unlike protons, electrons are point-like, so their collisions are clean and allow precision measurements. An electron-positron collider operating at 250 giga-electron volts would be a Higgs factory, producing millions of Higgs bosons and measuring their properties to fraction of a % precision. This would test whether the Higgs couplings match standard model predictions or show deviations indicating new physics. A muon collider represents a more speculative possibility. Muons are heavier than electrons but lighter than protons, offering a compromise between the clean environment of electron collisions and the high energy reach of proton collisions. Technical challenges include producing intense muon beams and handling their short lifetime. If these challenges are overcome, a muon collider could reach energies of 10 tera-electron volts or more while maintaining relatively clean collision environment. Regardless of which colliders are built, complementary experimental programs will be essential. Precision measurements of neutrino properties at dedicated neutrino experiments, like June and Hyperkamiokande, will test the neutrino sector of any beyond standard model theory. Searches for electric dipole moments will constrain CP violation. Measurements of rare decays, such as mu to E gamma, test lepton flavor violation. Direct dark matter detection experiments continue improving sensitivity. The interplay between different experimental approaches creates a web of constraints on new physics. A model that explains LHC anomalies must not conflict with neutrino oscillation data, flavor physics measurements, dark matter searches, or any of hundreds of other precision tests. This complementarity is a strength of the field, ensuring that claimed discoveries are robust and broadly consistent with all evidence. Theoretical work must keep pace with experimental progress. Developing new calculation techniques to push quantum field theory predictions to higher orders remains crucial for interpreting LHC data. Better understanding of non-perturbative QCD will clarify whether anomalies arise from underestimated hadronic effects or genuine new physics. Lattice QCD calculations of increasingly complex processes will provide independent predictions to compare with experiment. Machine learning is transforming both experimental and theoretical particle physics. Neural networks can identify subtle patterns in data that traditional methods miss. They optimize detector responses in real time. They generate simulated events orders of magnitude faster than conventional Monte Carlo. In theory, machine learning helps solve differential equations, find symmetries in Feynman diagrams, and explore parameter spaces of beyond standard model theories. The full impact of AI on particle physics is just beginning to be realized. Quantum computing offers potential future benefits. Simulating quantum field theories on classical computers becomes exponentially difficult as the number of particles and interactions grows. Quantum computers could potentially simulate quantum field theories more efficiently, enabling calculations currently impossible. While practical quantum field theory calculations on quantum computers remain far in the future, proof of principle demonstrations are beginning to appear. The sociological and organizational aspects of particle physics will also evolve. LHC collaborations involve thousands of physicists from hundreds of institutions across dozens of countries. Managing such large collaborations, ensuring fair credit attribution, and maintaining scientific standards requires sophisticated governance structures. As experiments grow even larger and more complex, collaboration models must adapt. Open data initiatives and reproducibility standards will become increasingly important. Funding for particle physics faces challenges as experiments become more expensive. The LHC cost approximately $10 billion. A 100-kilometre future circular collider would cost several times more. Justifying such investments requires not just scientific arguments, but also broader societal benefits. Particle physics drives technological innovation in detectors, computing, accelerator technology, and data analysis that finds applications far beyond physics. Making this case effectively to policymakers and the public is crucial for the field's future. Education and outreach play vital roles in sustaining particle physics. Training the next generation of experimental and theoretical physicists requires excellent graduate programs and postdoctoral opportunities. Communicating discoveries and their significance to the public builds support for the field and inspires young people to pursue physics careers. The LHC's success in capturing public imagination demonstrates the appetite for fundamental science when presented compellingly. The philosophical implications of fundamental physics remain profound. What are the ultimate building blocks of matter? Why do the laws of physics have the form they do? Is there a final theory that explains everything? Or is physics an infinite tower of more fundamental descriptions? These questions drive the field forward even when practical applications are distant. The pursuit of understanding nature at its most fundamental level represents one of humanity's highest intellectual achievements. The 95 giga-electron-volt resonance. Deep beneath the Swiss-French border, protons continue colliding millions of times per second. Detectors record the debris, algorithms sift through petabytes of data, and physicists worldwide scrutinize every distribution and every anomaly. What began as subtle statistical fluctuations has evolved into a pattern that refuses to disappear. The resonance at 95 giga-electron volts persists as data accumulates. The excesses in vector boson and heavy quark production remain consistent across independent analyses. The Lepton universality hints grow more intriguing with each measurement refinement. We stand at a moment reminiscent of the early 1970s, when small discrepancies in neutrino scattering data and peculiar events in cosmic rays were hinting at a hidden layer of nature. Those hints led to the November Revolution of 1974 with the discovery of the charm quark, followed by the bottom quark, the top quark, and eventually the Standard Model's completion with the Higgs boson. The current anomalies carry similar weight, subtle enough to demand caution, persistent enough to demand attention, and coherent enough to suggest an underlying pattern waiting to be revealed. By the end of Run 3 in 2026, physicists will have 3 times the integrated luminosity currently available. Statistical uncertainties will shrink. Systematic effects will be better understood. If the anomalies are real, they will cross the 5 sigma threshold decisively, marking confirmed discoveries of physics beyond the Standard Model. If they're fluctuations, they'll fade into statistical noise, joining the long list of tantalizing hints that didn't pan out. The implications extend far beyond particle physics. If new physics appears at tera-electron-volt scales, it connects to the deepest questions about the universe: the nature of dark matter, the origin of the cosmic matter, antimatter asymmetry, the unification of forces, and potentially quantum gravity itself. The anomalies, if confirmed, won't just add new particles to our catalogues. They'll provide the first experimental guidance in decades toward the theory that extends beyond the standard model, shaping physics for generations to come. As we await more data, one thing is certain. We're witnessing science at its most exciting, standing at the threshold of discovery, where careful measurement meets theoretical insight, and where the next collision might contain the clue that changes everything.